everyone. Today's live stream is an experiment, okay? So I decided to try and make this very long live stream explaining the entire structure one for IB chemistry students. It is working. Yes, okay, I'm muting myself. Right, so this is how it's gonna work. I will try to explain in one stream um, the entire structure one for SL and HL students, so particulate nature of matter, nucleus, electronic configuration, moles, and ideal gases, just following the syllabus, okay? And obviously, prepare yourself. Yeah, this is going to be a lengthy one. We'll see how it goes. I think I will have a break somewhere in between, but again, as I said, this is an experiment. So if you feel like you need these types of videos so that you like it helps you to study, then I have to know, okay? You have to show me somehow. You can hit the like button, you can subscribe, you can leave me a message or leave a comment. Because if I see engagement, I will continue. I will do structure 2, 3, and reactivities as well. If I don't see any engagement, then obviously there's no way I'm going to continue with these lengthy streams. Right. So in structure 1, most of the subtopics are for SL needed for SL students, but I will have a clear indication of which information is for SL, which information is for HL. It will be written on the top of the slide, you'll see, and also hopefully I will make some timestamps, and in the timestamps you'll be able to navigate through the structure and see which which parts are SL, which parts are HL. But again, the majority in this particular topic is just for SL. All right, so let's start. Yes, and by the way, you can ask me questions in the chat, but it's subscribers only mode. Okay, so if you want to ask a question, you have to subscribe and then I'll see your question. Okay, let's start. Right, so this is the slide, that's how it looks. You see the indication of SL and HL topics are here. Yeah, so this is SL and sometimes it will switch to HL. But again, I hope I will also indicate it in the timestamps. Well, let's start. So we start with particulate nature of matter, and let's go through some definitions. I understand that my video will cover some of the text. There's nothing I can do because I'm teaching with these notes, so I'm not going to redo the notes just for YouTube, so we'll just deal with that. If you need the notes, leave a comment and I'll send you the link to download it. So actually, maybe it's a good idea if you download this before you watch the stream, the recording of the stream, so that you can watch along and make notes together with me. All right, but if you're live, then just follow the notes. Okay, first structure. So first, a few definitions. That's structure 1.1. Yeah, a compound. It's a pure substance when two or more elements are chemically combined. So for a compound, you can have several elements, but they must be combined chemically through some type of bonding, covalent, ionic, or whatever. On the other hand, if you have a mixture, then the mixture is formed when two or more substances physically mix together. So there was this question, I think last year or last year. So in the mixtures, the components keep their individual properties, right? So if you mix, for example, water and salt, water would keep the properties of water, salt would keep the properties of salt. The mixtures can be split into homogeneous and heterogeneous. Homogeneous mixtures, they have uniform composition. So for example, again, if you have a solution of glucose in water or salt in water, it would look like water. That's why it's a homogeneous mixture, so you don't really see the different phases there. Heterogeneous mixture does not have a uniform composition and often consists of different phases. For example, if you have an insoluble salt in water, then you'll see it as two phases. That's a heterogeneous mixture. Or if you have, let's say, iron and sulfur, even though those are two solids, but still you can clearly see that there are two different substances in there. Let me check if I'm still alive. Yes, I am. Okay. It would be such a pity to make this humongous stream and then realize there is no sound. Well, let's do a couple of questions. So, which substances are compounds? So, air is the mixture of gases. So, not air, right? Air, it's like nitrogen, oxygen, CO2 mixture. Carbon dioxide, yes, it's a compound. Consists of two elements, carbon and oxygen, bonded chemically together through a covalent bond. Krypton is just one element, so not krypton, not a compound. Wood obviously a mixture. Ammonia compound consists of two elements, N and H. Iron element, glucose compound, milk mixture, gold element, methanol, carbon, hydrogen, oxygen chemically bonded compound, gasoline, it's a mixture, and we'll know it when we do organic chem. Now, which of the following mixtures are heterogeneous? To answer this question, you need to understand like the solubility of salts, which at this point, if you're just starting IB chemistry, maybe you don't know it yet, but I'll just tell you. So calcium chloride is soluble, that's why the mixture would be homogeneous, because you will see like one phase. AgCl is insoluble, so you would see the solid and liquid, so that's a heterogeneous. Sand and water, you know it, yeah, that's heterogeneous. Iron and sand, although two solids, heterogeneous. Air, homogeneous mixture, because you can't tell that there are two phases. There are no phases, they're just, everything is in gaseous state. A silver nitrate is soluble, so also homogeneous. These are not exam style yet, but it may be incorporated in some questions. Next, the next bit is separating mixtures. So to separate an insoluble solid from a liquid, we would use filtration. Okay, for example, if you need to separate sand and water, you have insoluble sand and water, so you would use the filtration, and this is the setup. So pay attention to the name of the apparatus. Okay, so we have a beaker with solid and liquid, then we have a filter funnel, so this thing is called filter funnel, and you see it's lined with filter paper. So filter funnel lined with filter paper, you pass the mixture through the filter paper, then a liquid would pass through, solid will be stuck onto the paper. That's filtration. So this you use to separate insoluble solid and liquid. Now, if you want to separate solid crystals from a solution, yes, so if you have a solution, a homogeneous mixture, and you want to take the crystals out, for example, if you have soluble copper sulfate dissolved in water, then you would use, I don't have the photograph, but you would use the process that is called crystallization. So for crystallization, what do? We take evaporating basin, also sometimes you can call it like it's the same as crucible, and you would place your solution into the evaporating basin, and if your salt is not decomposing upon heating, yeah, you can just heat the water out, heat the water, or the solution, the water will evaporate, and you will end up with crystals. Yeah, so to have crystals from a solution, you just evaporate the water, get the crystals. It could get a bit more complicated, even for GCSE, the process is a bit more complicated, but just the logic is there, right? Sometimes we cannot heat too much, because if the salt decomposes, then you can decompose the salt. So in that case, that's how we do it for GCSE, for example. You would heat to evaporate most of the water to make a saturated solution. Then you leave it to cool, and the crystals would form upon cooling down. Next technique is recrystallization. With this one, this is a new one in IB chemistry. Yeah, we didn't have it previously, so we don't have any questions on that. The technique is quite complicated, and they don't specify how much information you need to know about it. So I think this table is from A-level chemistry. So this is, if you really want to understand how recrystallization works, you can screenshot and read it, but I hope you don't need that many details for the exam, for IB exam. I think if you just know that recrystallization is used to purify organic solids, that could be enough. But again, if you want to be on the safe side, because I have never seen questions on that, well, except for like in practice papers, you can read and see how it goes. Yes, if you're aiming at a 7, definitely worth reading through and memorizing the steps. If not, well, recrystallization. So if you synthesize organic crystals, yeah, you do some reactions, you get organic crystals, then you evaporate the solvent, so you crystallize them, and then to make it purer, yeah, so to make your substance even more pure, what you do is you dissolve it again in the solvent and crystallize again. This is recrystallization, but it's not as simple as I explained it. Yeah, so these are the steps. If you want, you can read them. Next. The next technique is simple distillation. So for simple distillation, we use to separate a solvent from a solution. For example, if you have a mixture of salt and water and you don't need salt, you want to collect water, you could use this apparatus. So how does it work? So here you have your solution, and this is a gas delivery tube, and this is a condenser. So a condenser is just a glass tube with cold water circulating around. So you have a water supply of cold water in at the bottom, and the water would go out. So water in is at the bottom, water out at the top. And the condenser, like, it must be tilted, must be tilted, and the flow of water in that direction is important, because this way you ensure that your coldest part is here, and you also ensure that there are no air gaps or air bubbles in the condenser, so that you have a constant flow of water. So what happens here? So you heat with a Bunsen burner or with electric heater, and water evaporates, so steam is formed. It goes up to the gas delivery tube, and here you have cold water, which obviously condenses the steam. So steam is condensed, and you collect it into a new conical flask. This is how it looks in the lab. Probably you've done this experiment. So this is the heater, this is the condenser, this is water in, this is water out, and you collect water. It's the test tube is in the with the ice, so that it's it's condensed easier. Next one. This is, I think, the most common question. So this next separation technique is paper chromatography. Yes, let's see. So paper chromatography. So paper chromatography, it's used to separate mixtures of soluble substances. Often these substances are colored, or at least you can make them colored if you, for example, shine UV light, like with amino acids. So it could be, as I said, amino acids, it could be plant pigments, dyes, mixtures of inks. So you're separating some substances that are colored. How does it work? So these are the steps, like 1, 2, 3, 4. So first you take a chromatography paper. It looks like a filter paper, to be honest, especially in a school lab. Then you draw on the paper, you draw a pencil line. This would be your baseline. And on this baseline, you place your sample. The sample is a mixture of dyes, for example, a mixture of food colorings. Then what you do is you place this paper into a trough with solvent. Okay, this is the blue thing, is a solvent. Then the solvent would move up the paper due to capillary forces. So that's what happens. It moves up, and the dyes would move together with the solvent. Why would they do that? Well, it's because you have a mixture, right? And in that mixture, we expect the dyes to have different solubility in water and different affinity to the chromatography paper. So basically, they have different properties, and that's why they would have different solubility, and they would stick differently to the paper. So you would expect the colors to eventually separate. As the solvent moves up, the more soluble dye would travel further away. The less soluble would travel less. Or you can say that the better the dye sticks to the paper, the less it would travel. Right. So you wait for the solvent to reach like almost the top of the paper. Then you draw another line. This is your solvent front. So you would mark with the pencil where your solvent has stopped. Then you dry this out, and you end up with a chromatogram. So that's how it looks. So you have your solvent baseline, you have your solvent front, and you hopefully have separated dyes. By the way, the reason why we need this line to be in pencil and not in pen or whatever other thing you could use to draw it out, it's because you don't want the dye from your pen to interfere with the results, right? So if you make it with a pen, then the dye from the pen would also travel. Okay, and then what do we know from this chromatography paper? So from this chromatogram, we can find a so-called RF value. That's a retention or retardation factor. It's calculated as the distance moved by the substance from the baseline. So it's measured from the baseline to the middle of the spot. So this distance, for example, for green dye, divided by the distance moved by the solvent, so divided by this value. This is a very, very common question you could be asked to measure the RF value for different dyes. And then why do we need it? Well, essentially, if you compare RF value for a certain solvent with the data booklet values, you'll be able to tell, guess which substance, which dye you probably had. So RF value would be specific for a dye in that solvent. Of course, different dyes might have similar RF values, but that's a whole different story. Right. So let's see. So okay, that I said yes. So retention factor. Yes, and we said that RF value, it would depend on the solvent and it would depend on the paper that you're using. So what can they ask? So they could ask which component, green or red, is heavier. Yeah, by the way, that's another factor, right? So the heavier components would travel uh, less to lower distances, right? So since red dye traveled less, we can expect it to be heavier, probably. Yeah. Then which component is more soluble? Well, probably green because it traveled further. Also, we could say it's like more of a guessing game, right? But we can say that red dye sticks to paper better. Yeah, that's also one thing to notice. Okay, that was the separation techniques. Next again, standard level, states of matter, and we just need to know different phase changes, how they're called. So when you go from, well, obviously, yes, of course, you also need to know basic things that you know from MYP or from GCC, whatever you did before IBDP. You need to know that in solids, the particles are located close to each other. They are moving by vibrating about fixed positions, so not moving much. Yeah, so they're just vibrating around fixed positions. Then in liquids, the particles are more spread out and they can move, they can slide past each other. In gases, the particles have the highest distance between them, they move randomly, they move fast and occupy the entire volume of the vessel. So when you go from solid to liquid, that's melting. Everyone knows. When you go from liquid to solid, that's freezing. From liquid to gas, it's boiling or evaporating. From gas to liquid, that's condensing. So these phase changes, everyone knows the names, but then these everyone forgets. So when you go from solid to gas, that's sublimation. Solid to gas sublimation. So some substances, they would skip the liquid phase completely. For example, CO2, it can go from solid to gas right away. Then from gas to solid, that's deposition. Well, and guess which phase changes do they ask in the exams? Well, of course, sublimation and deposition mostly. Yeah. Let's see. So these are exam style questions from paper 1. Which equation represents sublimation? Sublimation, solid to gas. This is gas to solid. Doesn't work. Yeah, that's deposition. So not A. This is not a phase change. B is not a phase change. It's a chemical reaction. So not B. C is a chemical reaction. D works. Solid to gas sublimation. Yes, you see the phase changes are different. Which equation represents condensing? Okay, condensing. What is condensing? From gas to liquid. So we're looking for a phase change. Gas to liquid, it's A. Yeah. This is solid to liquid. That's melting. Then this is a chemical reaction, not a phase change. And this is gas to solid. That's deposition. Yeah, gas to solid deposition. Next one. The next bit, again, it's still 1.1 and still a cell. That's kinetic molecular theory. So in the new syllabus, they want you to know the formula for kinetic energy. For some reason, we never had questions on that, so I don't know what they might ask. But the formula is here, and I don't think it's in the data booklet. Let's actually check. It is not in the data booklet, but it is. They think that you should know it. So kinetic energy, it's the energy associated with movement of molecules. So it equals to 1/2 of mass of the molecule times speed times velocity squared. Yeah, and what can we know? What can we figure out from this equation? So kinetic energy is proportional to temperature, right? And if at a certain temperature, the molecules would have the same average kinetic, well, not the same energy, the average kinetic energy is kind of constant. So if you have a certain temperature, a fixed temperature, then the smaller particles, the particles with lower mass would move faster, or the particles with higher mass would move slower. Yeah, that's what we can figure out from this equation. But again, I don't know what they might ask. We'll see. We'll see when the exams are released. Yeah, so particles with smaller mass diffuse more quickly. Yeah, so they move quicker at the same temperature. The heating curve, again, that's a new part of the specification. We didn't have any questions, so it's again a guessing game what they might ask. But I think they would ask approximately the same things that they ask for SAT chemistry, because this is a very SAT chemistry style diagram. So, well, let's see. How does it look? So what is the heating curve? So heating curve, it shows how the temperature of the substance changes when you heat it, and also it shows the phase changes. So let's say we have a cube of ice, yeah, and we place it at negative 20 Celsius degrees. What is it? Well, it's a solid, right? That's a solid. Ice is solid at negative 20. Then we start heating it with the Bunsen burner. So as the time passes, we keep supplying heat. Yeah, so heat that we supplied increases, and we measure the temperature. Yeah, so we supply heat to a solid and see how its temperature changes. Well, okay, so we start at negative 20. At this point, we're heating solid. Yeah, so we supply heat, and that heat is used to increase kinetic energy of molecules, the average kinetic energy of molecules, which means that the temperature of ice would increase. Then at 0 Celsius, we reach a plateau, flat. Yeah, so it's flat. What does it mean? It means that we keep supplying heat, but the temperature does not increase. That's a phase change. That's changing. So ice starts to melt here. So you go from solid to liquid. And the heat energy that we're supplying, it goes to break intermolecular forces between water molecules. Right? So all the heat that we're supplying, it is used to break apart, to break those hydrogen bonds between water molecules. And that's why the temperature does not increase until the ice, like all the ice, melts into water. Now at this point it has melted, and then at this point we have liquid water. So this part of the curve, it's heating of liquid water. Again, we supply heat. That heat is used to increase kinetic energy of molecules. So average kinetic energy increases, temperature increases. Again, 100 Celsius plateau. Yeah. What happens here? Another phase change from water to steam, from liquid water to steam. The energy supplied is used to break intermolecular forces. Now, when all water turns to liquid water turns to gas, here we're heating steam. Yes, so again, the heat that we supply is used to increase the average kinetic energy of particles. So from this graph, I think what they can ask you to explain different parts of the graph. That's the first thing. And another thing is they can ask you to find melting and boiling points, right? So the first plateau, when you go from solid to liquid, that's a melting point. And this plateau, the next one from liquid to gas, that's the boiling point. Right. But again, no question, so we're not sure. And also you need to know how to convert temperature from Celsius to Kelvin and the other way around. So water freezes at 0 Celsius or 273 kelvins, and the absolute zero kelvins, it equals to negative 273 Celsius. So to convert from Celsius to kelvins, you need to take the temperature in Celsius and add 273. Yeah, that's the conversion. That's how you convert. And guys, very important, the temperature in kelvins can never be negative, okay? I've seen it so many times when I'm marking A levels. Temperature in kelvins, the minimum is 0, okay? If you say minus 100 kelvins, that's like I would you lose all the marks, okay? So 0 Kelvin is an absolute 0. It does not get lower than that. Okay, congratulations. We've done structure 1.1 and that took 24 minutes. Okay. Next bit, structure 1.2, nuclear atom, SL. So you see structure 1.1, it was all SL. This is also, most of it would be SL. Well, let's start. So structure of an atom. An atom consists of nucleus and electron shells. In the nucleus, we have protons, which are positively charged, and neutrons, which are, well, guess what? They're neutral, yeah, zero charge. In the electron shells, we have electrons. The proton have a symbol of P, relative mass, yes, so mass relative to something. So it's set as 1, then relative charge is +1, neutron symbol is N, relative mass is 1, charge 0, electron symbol E or E minus, either way is fine, and relative mass is very small compared to proton and neutron, and relative charge is -1. So some definitions. Protons and neutrons are also called nucleons. Then atomic number, it's called, well, it's the same as the number of protons. Yes, so that's the definition. So atomic number is the number of protons. The mass number, it's the number of protons plus the number of neutrons in the nucleus. And sometimes they would ask you to write down elements with this notation. So where you have the symbol of the element, and then at the top, only at the top, you would have a mass number. At the bottom, you would have the proton number or atomic number or the number of protons. And the number of protons, it equals to atomic number that could be found in the periodic table. For example, for carbon, 13 it's its mass number, 6 is the number of protons which is in the periodic table. Yeah, let me see. So there, atomic number. Also notice that in the periodic table in the IB, atomic number is written at the top, but in the notation, in the this symbol notation, you have to write it at the bottom. So it's always like that in all boards. You always write the number of protons at the bottom. What else is important? The top number, you can never take it from the periodic table. Okay, it might not match because in the periodic table this is not a mass number, this is relative atomic mass, so it's average throughout different isotopes, which we would talk about in a second. So the top number they would always give you in the question, or they would ask you to find from some additional information, but you cannot take it from the periodic table unless you're doing GCSE. But I hope GCSE students are not watching this stream, which just watch some other stream, okay? For GCSE students, the rules are slightly different because it's very simplified. But IB students, we don't take it from the periodic table A level as well. Right, okay, so Z, number of protons from the periodic table, that's atomic number. Number of electrons in the neutral atom, it would equal to the number of electrons, but only in an atom. Yeah. So for example, for this carbon, we have 6 protons, 6 electrons, because electrons are negative, protons are positive, so that the atom is neutral, we have to have equal amounts. And then the number of neutrons we find as the mass number minus number of protons. Yeah, so for this carbon, the mass number is 13. 13 minus 6 is 7. So it has 7 neutrons. Okay, I hope that's fine. Let's do this one. So how many protons, neutrons, and electrons are there in calcium 40? Well, let's see. Mass number is 40. Atomic number I find from the periodic table. Okay, calcium's atomic number is 20. So 20. Protons, 20 equals to atomic number. Electrons, this is neutral. Yeah, I don't have any charge here or anything, so 20 electrons. And neutrons, it's 40 minus 20. Not the best example, to be honest, but, well, we work with what we have. 20 neutrons. Next, sodium. Mass number 23. Number of protons from the periodic table. This is my sodium. It's 11. Yeah, protons are 11. So 11 protons, 11 electrons. Neutrons would be 23 minus 11, which is 12. Next one, barium 137. For that one, I'll need a calculator. Okay, barium, atomic number 56. So protons are 56, electrons are 56, neutrons are 137 minus 56. 137 minus 56 is 81. 81 neutrons. Okay, potassium, or maybe let's do potassium and we won't do sulfur. Potassium 39. Potassium 19 protons. Yeah, an atomic number is 19. Electrons are the same because they must be equal, it's a neutral atom. And neutrons 39 minus 19, which is 20. Right, done. Next, what do we do with ions? So ions are not neutral, so these are species that have lost or gained electrons. So when atom loses or gains electrons, it becomes an ion. Cations are positively charged ions. Remember, electrons are negative, so when an atom loses electrons, it gets the positive charge. So if we compare these two, so this guy, well, normally, yeah, 20 protons, 20 electrons, 20 neutrons. This one, 20 protons still, because atomic number. is the same. Then electrons are not 20 anymore because you see this charge. So 2 plus means that it lost 2 electrons. So 20 minus 2, it has 18 electrons. And, well, neutrons don't change. 40 minus 20. That's cations. For anions are negatively charged. So when atoms gain electrons, they become negatively charged. Let's see. So this sulfur, 16 protons, 16 electrons, because see, nothing is there, so it's neutral. And 34 minus 16, 18 protons. For this one, 16 protons, electrons, 16, that's from the neutral atom, plus 2. Yeah, because the charge is 2 minus, so 18. And neutrons are 34 minus 16, same, 18. Yeah, so if the charge is minus, we're adding electrons. If the charge is plus, we're losing electrons. Now, isotopes. Isotopes are atoms of the same element with the same atomic number but different mass number. That's the definition. Or you can say that isotopes have the same number of protons but different number of neutrons. So what's very important here? It's important to understand that the number of protons is what defines the element. So if you have 6 protons, it can only be carbon, nothing else. Yeah. If you have, let's say, 27 protons, it can only be cobalt, nothing else. But you can vary the number of neutrons, and that's why the mass number would be different. And that's why we have this relative atomic mass, which we would also talk in this huge live stream later. Yeah, so you see, for example, for carbon, it's not the atomic number is not 12, it's 12.01, which shows us that it has other isotopes, not just carbon 12. Well, okay. So for example, carbon 12 and carbon 14 are two isotopes. How do we know it? Well, because they have equal number of protons. Electrons, we don't really care about electrons for isotopes, but they have a different number of neutrons. This guy has 12 minus 6, so 6. This one has 14 minus 6, which is 8. So same number of protons, different number of neutrons. Okay, I hope that's fine. Now let's do this. So how many protons, neutrons, and electrons are there in N3 minus? Well, let's do this quickly for maybe 2 of those. So N3 minus, it has 14. The mass number is 14, so 14 is protons plus neutrons. Then I find protons from the periodic table. Nitrogen, was it nitrogen? 7 protons. So protons are 7. Well, yes, let's do electrons. Electrons are not 7 because the charge is 3 minus, right? So it's 7 plus 3 extra, so 10 electrons. And neutrons are 14 minus 7, so 7. Okay. Iron 2 plus. So 57 is the mass number. Now I'll find the number of protons. From the periodic table, iron 26. So 26 protons, electrons would be 26 minus 2. Yeah, because the charge is 2 plus, which means that we lost 2 electrons. So 24, and neutrons would be 57 minus 26. 57 minus 26 is 31 neutron. Good, good. Next, now we're off to mass spectroscopy, SL part. Okay, so with mass spectrometry, they don't really have now the apparatus that I have here. So essentially, I don't know. I think you are not supposed to know it, but I'm not sure because in the previous specification you were supposed to know it. So I'll explain it just in case, and because also it is easier to understand the future, what I'll explain in a few minutes, if you know approximately how it works. So mass spectrometry, it's a technique. Yes, so it's a technique that allows to identify isotopes in the sample. So what it will tell you is how many isotopes you have, what is the mass number of those isotopes, and what is the abundance of the isotopes in the sample of your element. Yeah, that's how it works. So let's say you took, I don't know, zinc or iron from somewhere from underground. So you extracted it somehow, yeah. However, however it works. So you have a sample, naturally occurring sample of iron, and then you vaporize it, and it goes into the mass spectrometer. The first step would be ionization. So you would bombard your sample with high energy electrons. And the electrons have such a high energy that they would knock off electrons from your sample of iron. Okay, so what happens is that those high energy electrons ionize, yes, so they turn your iron atoms into ions. So you would have a positively charged ions in this case, at this stage. And then those ions would be accelerated in electric field. Yeah, so they would start moving faster, they're accelerated, and then they would be deflected with a magnetic field by a magnet. And this deflection, uh, the level of deflection would depend on the mass and on the charge of your particle. Yeah, so if the let's say for simplicity, if all your particles lost one electron, so they have all 1+ charge, then heavier particles would be more difficult to deflect. Lighter particles would be easier to deflect. So this is how the mass spectrometer would separate particles by mass. Yeah, depending on how easy it is to deflect them. And finally, your deflected particles would reach would reach the detector. The detector is just a plate, and when the positively charged particles hit the detector, they pick up the electrons, and this creates current, right? So the flow of electrons in the detector, it's electric current, and well, obviously, the higher the current, the bigger the current you have, the more particles of that mass that you kind of identified there hits the detector. Yeah, so you would know the mass and the abundance. But again, you don't need to know a lot of details about it yet, just in general what happens. And this is a typical mass spectrum. So this is HL, okay? So this part, how the mass spectrum looks, that's the HL part. Yeah. But calculation would be for SL as well. So just don't switch, just have a look. Yeah, I think this is SL digestible. Previous years it was an SL. So this is how the mass spectrum looks. So we have a graph, basically a graph that shows us mass to charge ratio as x-axis, and percentage abundance, or just relative abundance. Doesn't have to be percentage, could be relative abundance, as the y-axis. So what do we know from here? So mass to charge ratio, what is that? That's the mass number of the isotope divided by the charge of the isotope at the point of ionization. Again, most of the time it would be +1. Sometimes they would have tricky questions. They would ask you to explain some additional peaks which are exactly twice less than the original peaks, and that's because it just happened to lose 2 electrons. Yeah, so the mass to charge ratio would be mass over 2. But again, we would do it when we have some exam practice. Now it's not crucial to understand. So from this mass spectrum, we know that we had, in our sample of zinc, we had 3 isotopes. So we have an isotope with a mass number of 64, and this is its abundance. So its abundance, it's 40%. We have an isotope with mass number of 66, and its abundance, it's approximately 30%. And we have an isotope of 67 with abundance of 30%. The sum is 40 plus 30 plus 30. It is 100, but it doesn't have to be 100, okay? So if they give you relative abundance, it could be any number. They could set this as 1, for example, or they could set this is 100%, something like that. Yeah, so don't assume that the sum of the abundances would be 100, not necessarily. Okay, now calculate the relative atomic mass of zinc from the mass spectrum given above. This I would treat as an SL question, but I will write the abundances and percentages. So the only difference between HL and SL here is that for HL they could give you the graph and you have to figure out the isotopes and abundance from the graph. For SL it would be either a table or they would give it to you in the form of just numbers, not a graph. Okay, so we have zinc 64. I'll just rewrite it. Zinc 64 with abundance of, was it 40%? And zinc 66, 30%. And zinc 67 is also 30%. Now, how do we calculate relative atomic mass? So relative atomic mass, it's the weighted average of all the isotopes. So essentially what I do is I just multiply mass number by abundance and add them all up. So 64 times 40. It's a bit noisy outside, but I think you can hear the car beeping. So okay, so I added them all up. Yeah, so 64 times 40, 66 times 30, 67 times 30, and then divided by the sum of the abundances. Again, do not assume that's 100. Could be 100. Well, in this case, it is 100, but always divide by the sum, whatever that sum is. Pretty straightforward. Okay. 64 times 40 plus 66 times 30, 67 times 30 over 100. So that's 65.5 or 50. They would tell you to how many decimal places to quote it. And also do a sanity check. So you got your relative atomic mass. Of course, it should be close to what's in the periodic table. Well, let's check. For zinc, it's, yes, 65.38, pretty close. Then also, your relative atomic mass cannot be lower than 64 and cannot be higher than 67. Yes, so it should be in between. Then also, it should be closer to 64 than to 67 because, or maybe actually, I don't know. Yeah, here it's hard to tell because these are 30. Yeah. Okay, just we know that it's in between 64 and 67. That's it. And this is also SL. Gallium has two isotopes, 69 and 71. The relative atomic mass of gallium is 69.72. And we're asked to calculate the percentage composition of naturally occurring sample of gallium. So this is like a reverse task. Yeah, so you're now given the relative atomic mass. I'll just give you time to read this. So you're given the relative atomic mass and you're asked to find the abundance. Well, let's see how we do. So we can just say that, let's assume that the abundance of one of the isotopes is X. So I would say that gallium 69 has abundance of X%, and then gallium 71 would have an abundance of 100 minus X%, because the total I set as 100. You can set it as 1 or 100, whatever. I set it as 100, so if one is X, the other one would be 100 minus X. And then do the same, so I know that relative atomic mass equals to, and then do the same as before, so multiply mass number by abundance. So I do 69X plus 71 times 100 minus X over the sum of the abundances, which I myself set as 100. That's 100, and then we just solve it for X. However, whatever method you use to solve equations, just use that one. I'll solve it, okay, I'll solve it like this, so I'll just multiply both sides by 100, and then I'll distribute the bracket, so that's 7100 minus 71X. Then I would move 7100 to that side with the minus, so that's 6972 minus 7100, and then this is minus 2x. Okay, 6972 minus 7100, negative 128 equals to 2x, to negative 2x, so x would equal to 64%. So our gallium, what did we put as x? We put gallium 69 as x. So our answer is gallium 69 is 64%, and then gallium 71, it's 100 minus 64, so that's 36%. And that makes sense, right? Because you see here it's easy to check. So your relative atomic mass is 69.72, which means that you should have a greater abundance of 69 isotope, right? Because your relative atomic mass is closer to 69 than to 71. This could actually also be a question. Yes, they might ask you to explain what does this relative atomic mass tell you about the abundance of the isotopes. Okay, SL question could be asked 2 or 3 marks, depending on how many isotopes they give. All right, let's check if I'm still live. Yes, I am. Okay. Next question. Do we have a question? No, next is atomic emission spectra, SL part. So let's talk about electromagnetic spectrum. So electromagnetic spectrum is given in the data booklet. That's all you need, all you need to know. Let's check it out. So it is here. So you don't have to memorize the spectrum, but they have, let's look at here. So they have increasing energy. So you know, for example, that infrared light has lower energy than UV light. And they also have increasing wavelength. So energy increases to the opposite direction to the wavelength. Yeah, so UV light is shorter wavelength than infrared, but they don't have frequency. So frequency you have to memorize. So frequency is increasing in the same directly proportional to energy, so it increases in the same direction as energy. Well, let's see. So I think even though it is in the data booklet and you can use it now for paper one as well, it's still good to know that UV light has a higher energy than visible light higher energy than infrared, and then inside the visible light, the blue light has the highest, well, the violet, yeah, light has the highest energy, red light has the lowest energy. Now let's make this virtual experiment in your head. So let's say you have hydrogen, okay? You put that poor hydrogen into gas discharge tube and supply voltage. Yeah, so voltage goes here. In the tube you have hydrogen. What would you see? You would see hydrogen glowing pink. Okay, experiment. Hydrogen glows pink. Now, if you collect that light and pass it through the prism, so the prism is just a magic device that splits light that you're passing through it into a spectrum. So if you pass, for example, white light through a prism, you would get a rainbow because white light consists of all the wavelengths, like visible wavelengths, right? But if you pass pink light that is emitted from hydrogen through the prism, you would not see a rainbow, you would see only certain colors. Yeah, and this kind of spectrum is called a line spectrum, as opposed to continuous with the rainbow. Yeah, so the rainbow would have been continuous, so this is a continuous spectrum. This is a line spectrum. Okay, experiment. Yeah, so hydrogen emits light when you supply voltage, and that light is not white. It is well, it emits only some frequencies of light, not all. Now let's explain it. We explain it this way. Yeah, by the way, what I said, it's written here, so just you'll be able to read it if you request the file. So I'll explain how that works. So if you have hydrogen, normally in hydrogen an electron would be at the ground state, energy level 1. Yeah, so this is where hydrogen's electron normally resides. Then when you supplied the voltage, that electron would jump up, so you excite the electron, it goes up somewhere up. And then when that electron falls back, the energy that it releases is emitted as a photon of light. Okay? So electron normally is here, then you do something, excite it, supply voltage, it goes up, then it falls back. And that difference in energy between energy levels, when it falls back, this is emitted as a photon. And that's why you don't see any wavelengths, right? You see some, because it cannot emit, for example, energy that corresponds to this. It cannot emit a photon that corresponds to this energy. Well, because it cannot be here. It doesn't have an energy level there. So it cannot jump between this point and this point. It can only jump between this and this, or this and this, like, yeah, it can only jump between energy levels. And that's why we see lines. That's why we don't see the rainbow or like continuous spectrum, because electron can only have discrete energy levels. Yeah. What else can we know from this spectrum? Some things that we just have to learn is that, well, obviously, the higher the energy difference between energy levels, the more energy is released, the higher the frequency of that photon. Yeah. And if an electron falls from anywhere to level 1, you would detect UV light. Okay? If it falls from anywhere to level 2, from anywhere above to level 2, you'll see the visible light. And if it falls from any higher level to level 3, you would see infrared light. Okay, yeah, so you would have 3 series here. I only wrote 2 series. So for example, if I have electron falling, you see from 2 to 1, that's UV light. From 4 to 1, UV light. Yeah, and if it goes from, let's say, 3 to 2, that's visible. From 4 to 2, visible, and so on. And now I explained why we have lines, right? Now let's explain why the lines get closer to each other. So if you look at the series, you see at higher frequencies, it is said that the lines are converging, so they get closer to each other. The reason for that is, or it's a proof actually, yeah, so it's a proof that energy levels get closer together at higher energy. So you see, the energy difference between level 1 and 2 is the highest. Between 2 and 3 it's lower. Then it gets lower and lower and lower. And that's why that the differences in frequencies would get smaller and smaller. Yeah. So you see, for example, let's say the frequency that corresponds to this photon with that energy. Well, let's say we plot it here. So this is the frequency, yeah, x-axis. Now, if you plot the frequency that corresponds to this energy, well, yes, they do have some energy gap. So they have a difference in energy. So they would have some difference in frequency. But then for this one, you see the difference between these two energy levels is small. That's why the difference between these two frequencies would also be smaller than between these two. Okay, so energy levels get closer together at high energies. That's why lines converge at high frequencies. Everything that I'm saying, guys, it's the mark scheme explanations, okay? You have to be very strict with your wording, very strict, because they you need to know which terms they want you to use, yeah. And that's why everything that is in the notes, everything that I'm saying, it's literally mark scheme explanations. All right, what else did I forget to say? Yeah, and I forgot to tell you about the convergence limit. So one more thing we need to know about the spectrum is that after some frequency you will stop seeing lines, yeah. So after this frequency there are no more lines detected, and this is called a convergence limit. So the convergence limit, it shows you basically the energy that is needed to remove an electron from an atom. So if you supply, if you, let's say you supplied voltage, yeah, electron jumps to a higher energy level. Because you don't see any frequencies after this point, it means that electron is not returning after this point. Yeah, so you supplied enough energy to ionize an electron. So electron, instead of jumping between energy levels, it flies away. Yeah, so the convergence limit in the UV series, the frequency of the convergence limit, it shows you the frequency for ionization energy, first ionization energy. Well, for hydrogen, that's the only ionization energy. Okay, let's quickly sum up. So, okay, so the fact that the hydrogen spectrum is a line spectrum tells us that there are energy levels that are discrete. The fact that the lines converge at high frequency tell us that energy levels get closer together at high energies. And the convergence limit, it tells us the energy, well, we can find ionization energy from the convergence limit. And also, if electron falls from anywhere to level 1, that's UV light. From anywhere above to level 2, that's visible light. From anywhere to level 3, that's infrared. Fine, fine. Okay, now this next bit is HL. That's calculations for oh, that's not electronic configurations. Actually, is it electronic configurations? Yeah, we moved into electronic configurations and I forgot to acknowledge that, which is good. We're now at structure 1.3. So yeah, okay, so atomic spectra calculations, HL, SL students can skip it. Hopefully by now you have the the timestamps, so just move on to the next bit. But HL students, you're staying, right? So atomic spectra calculations, we have some formulas in the data booklet. This is the first formula that is there. It's energy equals to, it's like how energy is connected to frequency. Energy is Planck's constant times frequency. But I think frequency is denoted as F, which is, where is that? Energy, yeah, it's denoted as F, but in my notes it's new, the Greek letter. Well, we can use this formula to convert between frequency and energy. Let's see the question. In hydrogen emission spectrum, the line that corresponds to the fall of the electron from the second to the first energy level has the frequency of that hertz. Hertz, it's the same as second to the -1. Yeah. What is the energy gap between the second and the first energy levels in an atom of hydrogen in joules? So units are important, right? Remember, whenever you're using Planck's constant, you can always double check the units in the data booklet, and also the constants are given there in table 2. So since Planck's constant is joules times second, it means that the energy that you get from this formula would be in joules. Well, let's calculate it. So we need energy. Yeah? So what is the energy gap between second and first levels? And we know the frequency for that line. So it's Planck's constant times frequency. So I do 6.63 times 10 to the negative 34 times frequency in hertz or seconds to the minus 1. The units are correct, so I don't have to do any conversions. 2467 times 10 to the power of 15. Alright, let's see. So 6.63 times 10 to the negative 34 times 2.467 times 10 to the power of 15 gives me 1.64 times 10 to the negative 18 joules. You can double check my calculations, and then if you find a mistake, you can just leave a comment for everyone to know. To know, yeah. 247,467 times 15, just double checking. Yeah, looks right. Okay, that's joules. That's the energy needed to remove one electron from one atom. And the next formula that we need to know is that frequency equals to speed of light over the wavelength. So that's the formula to convert between frequency and wavelength. So this is frequency of light in seconds or hertz. C is the speed of light. It's in the data booklet. I don't remember how many significant figures it's given, but just use whatever they have in the data booklet. That's 3 times 10 to the power of 8 meters per second, and lambda is the wavelength in meters. You see, meters are essential. Yeah, sometimes they would give you wavelength in nanometers. Remember that it's to convert from nanometers to meters, you multiply by 10 to the negative 9. And then let's see what is the question. So the question is, the wavelength of a line in the emission spectrum of hydrogen is 4.86 times 10 to the negative 7 meters, so the units are fine. Calculate the frequency and the energy of the emitted light. Well, let's calculate frequency. So we know the wave. So this is a lambda, yeah, that's wavelength. So I find frequency using this first formula. That's C over lambda. So I do 3 times 10 to the power of 8 over this 4.86 times 10 to the negative 7. And let's actually double check if we have these. Where do we have that? Yeah, that's table 2. So we have Planck's constant here, and we have what do we have? Do we have speed of light? Yes, we do there. Yeah, so 3.00 times 10 to the power of 8. Actually, three significant figures. 3 times 10 to the power of 8 over 4.86 times 10 to the negative 7. And practice to do these calculations on your calculator just to be sure that you don't mess it up in the exam. Because these are very easy questions and worth 2 or 3 marks, yeah? Okay, so we found frequency in seconds to the minus 1 or hertz. Now we can find the energy, calculate the frequency and the energy. Energy, it's h times frequency, so I do Planck's constant, which was 6.63 times 10 to the negative 34 times frequency times 10 to the negative 34 times 6.17 times 10 to the power of 14, which is 4.09 times 10 to the negative 19 joules. Yeah, well, that's what it is. Again, you can check the calculations. The next bit is also an HL, yeah, HL part. So the first ionization energy. Definition. The first ionization energy, it's the minimum energy required to remove 1 mole of the outermost electrons in the outer shell from 1 mole of gaseous atoms to produce 1 mole of gaseous ions, each with the charge of 1 plus. Like, this is the 100% definition. No one can ever you will never lose a mark on that. You can simplify it a little bit. Yeah, you can say energy needed to remove like 1 mole of electron from 1 mole of gaseous atoms. That's fine. But if you're writing it as an equation, the state symbols are essential, okay? So if you write, for example, X gas, yeah, so if you write this X solid or something, change the state symbol must be gases for both atoms and ions, okay? So you take X gas, that's your atom, remove an electron to form X plus gas, and an electron, E or E minus, doesn't matter. And also, this gas, it's true even for a metal. So even if something would never normally exist as a gas, for example, for sodium, the reaction for the first ionization energy, it's sodium gas goes to sodium plus gas and an electron, right? So sodium, you know it's a metal, but when you write ionization energy, that's how you should write it. So when we say the gaseous atom, we essentially just mean that it's alone, yeah, so it's on its own without anything around it, right? And remember we said that ionization energy, so that minimum energy required to remove one electron, then according to definition, we can find it from the convergence limit. Okay, let's see how we do that. Question. Calculate the ionization energy of hydrogen in kilojoules per mole. Yeah, this is the part where everyone makes mistakes. If the frequency of the convergence limit is, for the UV region, is that 3.3 times 10 to the power 15 hertz. Okay, so we know the frequency of the convergence limit. From there, we can find energy. But what energy would it be? This would be the energy needed to remove one electron from one atom, right? So this energy is per atom. We need it in kilojoules per mole. So essentially they ask how many kilojoules would you need to remove an electron from 1 mole of atoms. Well, let's see, what do we do here? So first I apply the formula, so that's Planck's constant. Okay, so Planck's constant, was it 663 or 664? I don't remember. 663 times 10 to the negative 14. Oh, I lost it. There. 63 times 10 to the negative 34, not 13, 34, times frequency 3.3 times 10 to the power of 15. Right. 6.63 times 10 to the negative 34 times 3.3 times 10 to the power of 15, which gives me 2.19. I mean, I won't, well, okay, I'll just do it to two significant figures. Not, that's not two, so the calculator value is 2.1879, so I do 2.2 times 10 to the negative 18 joules. So that's how many joules I need to remove one electron from one atom. That's per atom, yeah? And we want in kilojoules per mole. So first of all, we need to convert it to kilojoules, yeah? So it becomes 2.2 times 10 to the, so I divide it by 1,000, yeah? If I divide it by 1,000, it becomes negative 21, I think. Okay, let me just double check that. Negative 18 over 1,000. Yes, times 10 to the negative 21. So that's the same but in kilojoules. And then how do you convert it to kilojoules per mole? So if this is the energy you need to remove one electron from one atom, then the number of kilojoules you need to remove one electron from one, well, a mole of electron from a mole of atoms, it would be this energy times Avogadro's constant, which we haven't studied. But in this IB, the order in which we study topics, it's really funny. So I just followed the syllabus. So in kilojoules per mole, it would be 2.2 times 10 to the negative 21 times 6.02 times 10 to the 23rd. 2.2 times 10 to the negative 21 times 602 times 10 to the 23rd, which is 1,324 kilojoules per mole. If I did it right, yeah, but again, just double check. That's the calculator stuff. Fine, that's kilojoules per mole now. Next is successive ionization energies. Again, that's HL. So so we just talked about the first ionization energy when we remove the outermost electron. Now, if we can remove more electrons, right? So if you take your atom and keep removing electrons one by one, starting from the outer shell. Then the first ionization energy, it's when you remove the first electron, so that's X gas goes to X plus gas and an electron. Then the second ionization energy, well, it's when you remove the second electron from whatever was left. So you do X plus gas, then minus an electron. So you do equals to X2 plus and an electron, and so on. So you see the number of ionization energy, it corresponds to the number, to the oxidation state, or like the charge on the ion that you're forming. Yeah, okay. And the second ionization energy, or like every successive ionization energy, it would always be higher than the previous. Yeah. For example, let's explain why the second ionization energy is higher than the first. So it means that you need to supply more energy to remove the second electron than you need to remove the first electron. So, okay, let's see. So why? Explanation. When an electron is removed from an atom, a positive ion is formed, right? So when you remove the first electron, you're removing it from the neutral atom. But the second electron, you're removing from the positively charged atom, and positively charged ion. And a positive ion attracts negatively charged electrons more strongly than a neutral atom. That's the first explanation, probably 1 mark, yeah? Another way to explain it is that when an electron is removed, the remaining electrons would have a lower electron-electron repulsion. That's why they would be pulled closer to the nucleus, so more difficult, not pulled but attracted. Yeah, let's say attracted. The pulled is never accepted in the mark scheme, so let's say attracted closer to the nucleus, so more energy is needed to remove them. Right. Okay. That's the explanation for the second ionization energy, and like all consecutive ionization energies. Now again, this is still HL, guys. Yeah. So HL. Now let's take an atom. Let's say chlorine. Yeah. So I have an atom of chlorine here, and let's see how the trend, like how the ionization energies would look if we plot them on a graph. So this is like a very simplified electron structure for chlorine. So it has a nucleus here, and it has 7 electrons in the outer shell, 8 in the middle shell, and 2 in the inner shell. And when we remove electrons, we start removing from the outer shell. So this would be the first electron I'm removing. This is the second, third, fourth, fifth, sixth, seventh, and then the eighth electron from the second shell, ninth, 10th, and so on. Yeah, so you got the idea. So the number, it shows you the number of electron, like in which order we're removing them. And let's plot ionization energy for every electron we are removing. And this is how the graph would look like. So if you plot a graph, log of ionization energy, or just ionization energy, against electron number. So when we remove the first electron, let's say ionization energy is there, some log of ionization energy is here. Now, when you remove the second electron, it slightly increases. Yeah, because as we said, less electron-electron repulsion, or the ion, you're removing an electron from the ion now, so any explanation would work. Then from the third one, okay, again higher. So you see, from electron 1 to electron 7, ionization energy gradually increases. But then what do we see? Then we see the jump in ionization energy between electron 7 and 8. Why does that happen? Well, if we go back, you see the 7th electron is removed from the outer shell, but the 8th electron is removed from the shell that is closer to the nucleus. And electrons are negative, they're attracted to the nucleus. So the 8th electron is much closer to the nucleus than the 7th. That's why it would be attracted much stronger, and that's why you see the jump. So these these 7 electrons, they were removed from the third shell. Yeah, then you see the jump when you change the shell. These electrons are removed from the second shell, and the last 2 electrons are removed from the first shell. So you see 2 jumps here, the first jump and the second jump. Using the first jump, you can find out how many electrons you have in an outer shell. So you see you have a jump between electrons, ionization energy 7 and 8, which means that your atom has 7 electrons in its outer shell. Yeah, you see 2 jumps in total for the entire atom, which means that you know that it has 3 shells, because this is shell 3, this is shell 2, this is shell 1. All right. Yes, and this is how you explain. Yeah, for example, they would ask you, explain which group this element like, in which group does this element belong in the periodic table, you say there is a jump between ionization energy 7 and 8, which means that 7th electron is removed from the outer shell, the 8th electron is removed from the shell that is closer to the nucleus, which means that it has 7 electrons in the outer shell. Yep, that's your 2 marks explanation. Well, it means that it's group 7 if they ask to identify the group. All right, and then again, HL part. Let's talk about first ionization energy periodicity. With this part of the syllabus, I am not sure because it's also in structure, in some other structure, 2 or 3, like where the three I think, where the periodic trends are. I will explain it here because according to my students, most of the time this is asked in structure 1. So I'll just explain it here just in case if you're preparing for the test. But again, we'll do it again in some other, I forgot, was it structure 3? I think it's structure 3. All right, so let's talk about first ionization energy periodicity. So it's how the first ionization energy changes across the period and down the group. So let's talk about, well, let's, for example, look at sodium. So sodium has 3 shells, and we're removing this outer electron from the 3rd shell. Yeah. Now let's see what happens when we go down the group. So down the group, the first ionization energy would decrease. What does it mean? It means that it becomes easier to remove an electron. So, and we explain it based on the factors that affect the attraction of our electron to the nucleus. Yeah, so what affects our attraction? The attraction is affected by the nuclear charge. So obviously, the more protons you have, the stronger the electron is attracted. And also what affects it, it's the number of electrons in between. Yeah, so electrons are negative. So the electrons that are in between our nucleus and outer electron, they also affect the attraction of this red one to the nucleus, right? Because they offset the charge of the nucleus. And these electrons from the inner shells, they're called the screening or shielding electrons. Yeah, so charge of the nucleus, shielding, and also another factor that affects the attraction, it would be the distance of this electron from the nucleus. Yes, so the further away it is, the easier it is to remove. Well, keeping in mind those 3 factors, let's see. So as we go down the group, nuclear charge increases, yeah, because we get more protons as we go down the group. So we would think that probably that means that it becomes more difficult to remove an electron. But what else changes? The number of screening electrons also changes. Let's see if I have this. No, I don't have it. Okay, so as you go down the group, you're adding shells, right? So the number of screening electrons would also change, which would compensate the increase in the number of protons. Okay, so the nuclear charge increasing, but the number of screening electrons also increases. These 2 effects cancel each other out, and the only other factor that's left is atomic radius. So as you go down the group, atomic radius increases, so which means that outer electron is further from the nucleus, so ionization energy decreases. This question could be either 1 mark or 3 marks, okay? So if it's 3 marks, you have to say that, you have to explain that nuclear charge increases, but screening also increases. These 2 effects cancel out, so the only other factor is radius, which is increases. So electron is further from the nucleus, experiences weaker nuclear attraction. That's 3 marks. If it's 1 mark, you can just say that the atomic radius increases, electron is further from the nucleus, right? And weaker attracted. That would be just for 1 mark. Now let's talk about the trend of the first ionization energy across the period. This would not make a lot of sense if you haven't done electron configuration yet, and in this video we would do it later. That's how the IB syllabus works. Yes, I'm just following the order. So if you don't know electron configurations, maybe it's worth doing that first and then go back here. But let's see. Hopefully you already have some idea about the configuration. So, okay, so across the period, again, there could be 2 types of questions. They can ask you about the general trend in the first ionization energy across the period, or they could ask you to also explain the exceptions. So the general trend is that the first ionization energy increases across the period. Yeah, so as you go across the period, it becomes more difficult to remove the outer electron. Yeah, so that's first ionization energy increases. Same reasons as well, same factors as before. So as we go across the period, the nuclear charge increases, but the shielding or screening is approximately constant because there are the same number of shells. Yeah, so all period 3 elements, they have 3 shells, so the screening comes from shell 1 and 2. So nuclear charge increases, shielding is approximately constant, which means that outer electron experiences stronger nuclear attraction as you go across the period. Yeah. But there are exceptions. If we plot the first ionization energy for period 3 elements, for period 2 it would work in exact same way. You see that, okay, generally, yes, it increases, but then there are two exceptions, which are aluminium and sulfur. So aluminium is not following the trend. We would expect it to be above magnesium, but it is below. Same for sulfur. We would expect it to be above phosphorus because it has an extra proton, but it is below phosphorus. And let's explain why. To explain why, we need to see which electron we are removing. So we're removing the outermost electron. For sodium, if you write electron configuration, which I will explain later. Yeah, so again, a little confusing, but you can go watch electron configuration part first. I have the timestamps, hopefully. I have them by now. And you can watch that and then go back if you want to. But if you know electron configurations, I'll explain. So, okay, so for sodium, electron configuration is 1s2, 2s2, 2p6, 3s1. For magnesium, 3s2. For aluminium, 3s2, 3p1, then 3p2, 3p3, 3p4, 3p5, 3p6. Okay, so this is the outer shell basically. Yeah. Okay, so when you go from sodium to magnesium, for both you're removing the 3s electron. Magnesium has one extra proton. Everything works well. Yes, so you just increase the ionization energy because of the higher number of protons. Then when we go to aluminium, what electron are we removing? We're removing the 3p electron instead of 3s. And 3p subshell has higher energy electron. Yes, so 3p electron has a higher energy. And also 3p subshell, it's a little further from the nucleus, and it also experiences a little bit of extra shielding from 4s. All of these factors, they overpower the extra proton. Yeah, so they weaken the nuclear attraction. And so even though aluminium has that extra proton compared to magnesium, what I just said, that the electron has a higher energy, that p subshell, 3p subshell is further from the nucleus than 3s, that experiences extra shielding, all of that um, decreases the ionization energy. Then for silicon, we're removing p electron and just adding a proton, so all works. Phosphorus again, 3p3, all works. Then why sulfur is an exception? So for sulfur, we're also removing 3p electron, but let's look at that electron. So again, this is what I will explain a bit later. So for phosphorus, we said that it's 3p3, sulfur is 3p4. So if we draw out the boxes with arrows notation, yeah. So in phosphorus, 3p electrons are all unpaired. For sulfur, 1, 2, 3, 4. You see the fourth electron is paired. So in phosphorus, we are removing an unpaired electron. For sulfur, we are removing a paired electron. And that's exactly the wording that you have to use. Yeah, so paired, unpaired, not doubly occupied, not paired orbital. I've seen so many weird answers in exams. Yeah, so not doubly occupied, not singly occupied, not paired orbitals, not paired subshell, paired electrons. Okay, sulfur has a paired electron, but it has paired electrons in a 3p orbital. Yeah, that's how we do it, but I'll talk about it when we do electronic configuration. Yeah, so despite the fact that it has an extra proton, the repulsion between the paired electrons would make the first ionization energy lower than that in phosphorus. Okay? Okay, so paired electrons, extra repulsion. For sulfur, lower first ionization energy than expected. For aluminium, electrons removed from another subshell, which is further higher, has a higher energy of electron and extra shielding. That's why it's lower. All right. Electronic configurations, SL. Let's see how much we have left. So I think it's it's 20. So we're halfway through. I think we're halfway through, and it's been 1 hour 20 minutes. Okay, let's see how much I can go. I think we'll have a break maybe after electron configuration. We'll see. Yeah, hopefully. Okay, electron configuration. So we looked at the nucleus. Yeah, we said that okay, there are protons and neutrons. We learned how to calculate them. Now let's look at electrons. So electrons are arranged in shells. Yeah, shell 1, it's closest to the nucleus and it has the lowest energy. Shell 2 is further. Shell 3 is even further. And we know that there are shells from the emission spectrum. Yeah, so we experimentally kind of shown that that's how the atom looks, how it works. The maximum number of electrons in the energy level, so shell is also called energy level. So the maximum number of electrons in the energy level equals to 2 times n squared. You don't really need the formula, but some people really like to use this formula. If you memorize it, it's good. If not, just, write configuration and calculate. That you don't really need it. It's not in the data booklet. But if you want to use it, so that's the formula that shows the maximum number of electrons in the energy level, where n is the number of the level. Then, if we look in more detail, so energy levels are split into sublevels. The sublevels are denoted as S, P, D, and F. Yeah, SPDF, that's how you name the sublevels. And the maximum number of electrons in the S sublevel or subshell, sublevel, subshell, that's the same thing, is 2. Yeah, so S sublevel can have 2 electrons, P sublevel can have a maximum of 6 electrons, D a maximum of 10, F a maximum of 14. Okay, random facts to memorize. So if we look at how this works, yeah, so level 1 has only one subshell, 1s. The blue one is level 2. Level 2 is higher than level 1. It has 2 subshells, 2s and 2p. Level 3, the black one, it has 3 subshells, 3s, 3p, 3d. Level 4 would have 4 subshells, which I didn't write here. Yeah, 4s, 4p, 4d, and 4f. And if you look that within one energy level, the sublevels always go in order of S, P, D, F. So S would always have the lowest energy in that shell, yeah, in that level. P higher, D higher, F higher, if it's even there. But then between the levels, the subshells can overlap. So you see 4S from the fourth energy level, 4S subshell from the fourth energy level, it has a lower energy than 3D sublevel from the third energy level. Yeah, and you have to be very careful when you're using the terms. If you say 3s level, you lose a mark. If you say first subshell, you lose a mark. Yeah, you have to be really careful with how you like. If it's SPD, you say subshell or sublevel. If it's 1, 2, 3, you say level or shell. Okay. And the next bit that brings us to Aufbau principle, that's the order of electron orbitals filling. So electron orbitals would fill from lower energy to higher energy. So that's the order. 1s, then 2s, 2p, 3s, 3p, 4s, 3d. Yeah, you see, remember, d higher than 3d is higher than 4s, so that's why it goes like that. 4s, 3d, 4p, 5s, 4d, 5p, and so on. If you have problems memorizing this order, what you could do is you could use this diagram. So you put 1s, 2s, 3s like in a column. Then from the second level, so you see where you have 2s, you start the p. Yeah, so you go 2p, 3p, 4p, 5p. Then at the third level, you start the 3d subshell. So you go 3d, 4d, 5d, and so on. And then you can do it for f as well. But you will never need for f for IB. And then you zigzag the thing. So you see, you start from here. So 1s goes first, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, and so on. Yeah, and so on until you reach whatever you need. But in IB, I think the highest you can go is up to iodine. I think I've never seen anything above 53. You never know, but hopefully they would not change the tradition. Right, and also remember that s orbital can have a maximum of 2 electrons, p a maximum of 6, d is a maximum of 10. They don't necessarily have to fill all of the orbitals, yeah, but all of the subshells, but that's the maximum. So s, I will write it down here, maximum is 2, p maximum is 6, d maximum is 10, f 14, but there. F is 14, but hopefully we will not need it for the configurations. Alright, well, let's write down electron configuration of selenium. So to write down electron configuration of selenium, we have to find out the number of electrons, which we already know how to do. We go to the data booklet, find selenium, and find out that it has 34 protons, which means that it has 34 electrons. And then write down the configuration. So I start filling in the orbitals in that order. So I do 1s, the maximum number on the s orbital is 2, 1s2. Then I do 2s2, 2p6, yeah, the maximum number on p6. So I wrote it up to here. I have accommodated 10 electrons, 2 plus 2 plus 6, out of 34. So I continue. 3 in that order, 3s2, 3p6, 4s2. Let's see how much I have now. It's 10 plus 2 plus 6 plus 2, so it's 20 electrons I have accommodated so far. The next one is 3d10, so now I have 30 electrons. And then the next one is 4p. P can hold a maximum of 6 electrons, but we don't need 6. If I put 4p6, I would have 36 electrons in total, which is more than what I need. So I will end up with 4p4. So that the sum, so if you check the sum, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 4. That's the sum of these is 34. So 34 electrons in the whole structure. Now, this was the full electron configuration. Sometimes they would ask you to write down the condensed electron configuration. For the condensed electron configuration, you write the full configuration first, and then you would substitute some part of the electronic configuration with the closest previous noble gas. Okay, so for example, for selenium, let's look at the periodic table. So that's our selenium. There it is. So the previous closest noble gas would be argon. Okay, so I will substitute the first 18 electrons with argon in the square brackets. So that was the configuration, yeah, and then the first 18 electrons, so it's this part, yeah, that's 2 plus 2 plus 6 plus 2 plus 6, that's 18 electrons. So these 18 electrons I'm substituting with argon in the square brackets, and I leave what's left, 4s2, 3d10, 4p4. So that's the condensed electron configuration. Now let's talk about exceptions. So for IB, you need to know two exceptions in the filling of the orbitals. So it's chromium and copper. Chromium has atomic number of 24. Copper has atomic number of 29. So when you go and when you try to write down electronic configuration for chromium, what do we do? Well, let's write it down for 24 electrons. So I go 1s2, 2s2, 2p6. So far I have 10 electrons. 3s2, 3p6, then 4s2, that's 20. 3d4. So this is what you would end up if you write it normally, yeah, following Aufbau principle. Now chromium is an exception, and they say it's an exception because exactly half-filled 3D is more stable, like is very stable, has some extra stability and stuff. So that's why instead of having 4s2 3d4, you would have to promote the 4s electron to the 3d. So instead of 4s2, I would have 4s1 3d5. So I didn't change the total number of electrons, okay? It's still 24, but instead of 4s2 3d4, I write 4s1 3d5. And the next exception is copper. Let's do the same. So it has 29 electrons. So the configuration, if I write it normally without knowing it's an exception, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's 1023, d9. Yeah, so that's how I would write it if it was 3d9, I mean. Yeah, 3d9, if I didn't know it was an exception. But again, they say that exact, like fully filled 3D is super stable, so that's why instead of 4s2 3d9, I would write it as 4s1 3d10. So again, I'm promoting an electron from 4s to 3d. All right, yeah, that's it. And this is the condensed configuration, so please remember about that. Let's practice a little bit and let's write a few configurations here. So write the full and condensed electron configurations for sulfur, chromium, phosphorus, iron, copper, chlorine. Well, let's do some of them. Not all. Let's do sulfur. Yeah. So for sulfur, I find it in the periodic table and find the number of electrons. So sulfur has 16 electrons. So I do 1s2, 2s2, 2p6, that's 2 plus 2 plus 6, that's 10 electrons so far. Then 3s2, 12 electrons, so then 3p4p, I need 4 left. Yeah, so 3p4. That's full electron configuration for sulfur. 10, 16 electrons. Then to write down the condensed configuration, I have to substitute part of the formula with the noble gas. So I go back to the periodic table. Sulfur, there it is. The closest previous noble gas is neon with 10 electrons, which you cannot see because I'm blocking the view. There it is. Yeah, so I would substitute the first 10 electrons with neon in the square brackets. So the first 10 electrons are these. Yeah, so that becomes neon 3s2 3p4. That's the condensed configuration. And let's do one more maybe for iron. Let's do Fe. So for Fe, it has 26 electrons. 26 electrons. So we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, yeah, 1026. And then for the condensed configuration, I go to the data booklet, check the closest previous noble gas is argon with 18 electrons. So I would substitute the first 18 electrons, which are these guys. Yeah, that's 10, 18. Yeah, so that's argon, 4s2, 3d6. Okay, that's the condensed configuration. And in the questions, be very careful what they ask you for. So they might ask you for full configuration, then you lose marks on the condensed. If they ask you for condensed and you write the full configuration, you also lose a mark. Now the orbital. So okay, so we understand that there are energy levels, there are energy sublevels, and now if we zoom in, we'll see that there are orbitals. So orbitals are basically regions of space that are occupied by electrons. Yeah, and we need to know the shapes of the orbitals. So we need to know that s orbitals are spherical, p orbitals are dumbbell shaped, and there are three types of p orbitals. So px, py, and pz. So this is pz orbital. So it's a dumbbell shaped orbital that is aligned with the z-axis. Px is aligned with x-axis, py with y-axis. Right. And in S sublevel, there is always one orbital. In P sublevel, there are always 3 orbitals. In D, 5 orbitals. In F sublevel, 7 orbitals. And each orbital can hold a maximum of 2 electrons. Okay, and that's why, like, if you multiply these numbers by 2, you would end up with the maximum number of electrons in the orbital. Now, the orbital diagrams are represented with squares and all boxes and arrows. Yeah, so if we this is like a approximate summary of the orbitals in energy subshells. So you see 1s subshell, or the first energy level, it has only one orbital. Then 2s, it has one orbital. 2p subshell, it has 3 orbitals, and so on. Yeah, so so if you have s subshell, you always write it as 1 square. If you have p subshell, you always write it as 3 squares. D subshell, you always write it as 5 squares. And when we fill, we know how we fill it. Yes, so we fill it from the lowest to the highest energy. Yeah, so we have this to fill in the orbitals. And to draw this arrows in the boxes diagrams, we need to know 2 principles. Pauli exclusion principle says that the maximum number of electrons in an orbital is 2, which we just discussed. And when there are 2 electrons in the orbital, they must have opposite spins. So you would draw 1 electron facing up, 1 electron facing down. You don't need to know what the spin is, but just every electron has to be different in an atom, so we denote these 2 electrons with different spins. Then we also need to know Hund's rule. It says that electrons fill the orbitals of the same energy to have the maximum number of electrons with the same spin. So what it means in easy terms is just that if you have, for example, in p subshell, you have 3 orbitals with exact same energy, so you fill electron 1 per orbital first, and then if you need to, you start pairing them up. Okay, let's draw an orbital diagram for sulfur. For sulfur and maybe for something else. Let's do it for maybe, well, let's do it actually for an exception, for chromium. Yeah, let's do that. All right. Well, let's see. Let's do it for sulfur. Sulfur, we already know the configuration. We just did it. So it was 1s2, 2s2, 2p6, 3s2, 3p4. And now I will draw out the orbitals. You could draw them as I did here. Yeah, so you could draw them showing the energy. So lower energy, then higher and higher. Usually in the questions, they would either like have the printed version of the squares, yes, so that it goes in increasing energy. If they don't have the printed version of the squares, then you can write them in one line for IB. That's fine. So 1s, s is always 1 square. 2s, again, it's s, so 1 square. P, 2p, p is always 3 squares. 1, that's a 2. 2p, then 3s, again s, so 1 square, and 3p. Yeah, so I put the number of squares based on what subshell it is. For s it's 1 square, square is an orbital, yeah. For p it's 3 squares, and for d would have been 5. Well, and I start filling. So I'm filling 1s. I put one electron first facing up, like spin up, the other one facing down. Next, 2s, 2s2, so 2 electrons, one up, one down. 2p6. Okay, so strictly speaking, for p electrons, I have to put electrons one per orbital first. So I would do 1, 2, 3, but I need to accommodate 6 in 2p, so then I start pairing them. 4, 5, 6. Yeah, obviously you know that the whole orbital, like the whole subshell, has all paired electrons, so you can just draw them however you want, but just keep in mind that electrons would fill an orbital one at a time, and then they would start pairing. 3s2, 3p4, so 1, 2, 3, and then I start pairing 4. That's the orbital diagram for sulfur. Let's do one for chromium. Do I have space? Well, I'll try to fit it in. So chromium. Remember, chromium was an exception. It has 24 electrons. Yeah, there it is. So it would be 1s2, 2s2, 2p6, 3s2, 3p6. Then if I wrote it normally, I would say 4s2, 3d4, that's 24 electrons, but we know it's an exception, so I write it as 4s1, 3d5. Yeah, okay. And now let's do the boxes thing. So 1s, 2s, 2p, well, p is 3, yeah, 3s, 3p, 4s, 3d. D is 5 squares, 5 orbitals. 1, 2, 3, 4, 5. And then I start filling them in. So 1s2, 1, 2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 3s2, 1, 2, 3p6, 1, 2, 3, 4, 5, 6, 4s1, so 1 electron, 3d5, 1, 2, 3, 4, 5. That's my electron configuration, orbital diagram for chromium. Okay, the next bit, electron configuration of ions, and I think that's the last one. Yeah, and then we can have a break, and then we do molten ideal gases. Electron configuration of ions. So whenever you have cations, remember we remove electrons from the outer shell. Okay. So for example, for magnesium, 1s2, 2s2, 2p6, 3s2. So the outer shell, it's 3s. So magnesium 2 plus, I remove these guys. So it's 2p6. For gallium, 4s2, 3d10, 4p1. If I need to make gallium 3 plus, I'm removing the outer shell electron. So I remove 1 electron from 4p and 2 electrons from 4s. 3d is the third energy shell, third energy level. I'm not removing 3d yet. Yeah. If I need to add electrons, like in Cl-, I'm adding to the outer shell. So if chlorine is 3d5, then Cl minus would be, 3p5, Cl minus would be 3p6. I've added an electron. All right, and let's write, let's write the electron configuration for iron 3 plus, and then have a break. So for iron 3 plus, whenever, especially when you have transition metals, when you have to write electron configuration, always write the configuration of an atom first and then remove electrons, because 4s electrons are removed before the 3d. Okay, so you would remove 4s before 3d, and so that's why if you just say that, for example, iron instead of 26 has 23 electrons, you would remove the wrong electrons. So just do it for iron atom first and then for iron 3 plus. So let's do it for iron. Iron 26 electrons, we already wrote it down. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's 20 electrons, 3d6. Yep, that's electron configuration of iron. Now to make it iron 3 plus, what do? We first remove the 4s electrons. So I will remove the two 4s electrons. There are two, so I can remove only two. And the third one would go from 3d. Okay? So the configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s0, you don't have to write it, yeah, but I removed the 4s, and 3d5. Okay, so 4s are removed before 3d. That's the electron configuration. Okay, we did it. That was structure 1.1 to 1.3. That was actually my initial plan, to just cover that today because it's already 1 hour and 40 minutes. But I also want to cover moles and ideal gases. But I need a break. I need a break to drink some tea. So I will just put an announcement that it's a break, and I will see you in 5 minutes. And if you have any questions, you can think about them and post them in the chat. Okay, see you in 5 minutes. Okay, I'm back. I refreshed. Let's see if everything's working. I hope everything's working. I'll just double check my sound. Yes. Okay, all working. All right, so let's continue. Um, all good, right? I hope everything's fine. Uh, let's see. So, next, we are moving on again, structure one, moving on to moles. Yeah, mole section. That is an SL topic. So, definition. Yeah, so mole, it's the amount of substance that contains 6.02 times 10 to the 23rd number of particles. Well, that number of particles. And this number, it's called Avogadro's constant. So moles, it's like one of the most complicated topics for some reason and the most commonly asked. So you can think about a mole as a counting number. So if you say a pair, you mean two. If you say a dozen, you mean 12. Well, if you say a mole, you mean that 6 times 10 to the 23rd. You can have a mole of anything, a mole of molecules, a mole of atoms, mole of ions, whatever. Yeah, mole of apples, just a counting number. Let me check. Yes, all good. Everything is working. And next, so let's see. So how many molecules are there in 1 mole of water? Well, we know that 1 mole is just Avogadro's constant, so that's 6.02 times 10 to the 23rd. If it's 2 moles of water, well, then it's 2 times 6.02 times 10 to the 23rd. I won't even calculate this, okay? It's just very straightforward. If it's 0.5 moles of SO2, well, guess what? That's how many molecules you would have. All right, that's clear. Then a bit more complicated questions. Of course, in the exams you'd have them a bit more complicated. So if we had 2 moles of H2SO4 molecules, yeah, so H2SO4 is a molecule. If we had 2 moles of these molecules, what would we have? So we can find out the number of hydrogen atoms, yeah. So in one molecule you have two hydrogen atoms, right? Because you see it's H2SO4. So in 2 moles of H2SO4 molecules you would have 2 times 2. So it's 4 moles of hydrogen atoms. Or then you can convert them to atoms, to the number of atoms, or 4 times Avogadro's constant, yes, so that many hydrogen atoms. Then if you have 2 moles of H2SO4, how many moles of sulfur atoms would you have? Well, same. Yeah, it's also 2 moles because it's 2 times 1 because each molecule of H2SO4 has 1 sulfur. So you have 2 moles of sulfur atoms or 2 times Avogadro's constant, so that many sulfur atoms if you were to count them. Then if you have 2 moles of H2SO4. In those 2 moles of H2SO4, you have 2 times 4, so 8 moles of oxygen atoms. And you can multiply it by Avogadro to have the number of oxygen atoms. So it's very important to understand what exactly do they ask. Do they ask you about the number of moles of atoms or whatever? Or do they ask you about the number of atoms or molecules? Yeah, so if it's the number of moles, the number is small, you would have like 2, 1, 0.5. If it's the number of atoms, usually it would be large. Yeah, it would be 10 to the power of something. Okay, let's see the exam style question. So, question. Okay, you see it. What is the total number of carbon atoms in 0.2 moles of glucose? And the answer. So, since that's the number of atoms, I know it can't be 1.2. Yeah, it must be a big number. So, something A, C, or D. Okay, let's see how do I do it. So they want the total number of carbon atoms. So in 0.2 moles of glucose, I would have 0.2 times 6 moles of carbon atoms. Yeah, so this is moles of carbon atoms. And then I multiply it by Avogadro's constant to find the number of atoms. So it's 0.2 times 6 times 6.02 times 10 to the 23rd. 7.224 times 10 to the 23rd, so that is C. What is the total number of oxygen atoms in 1.5 moles of Na2CO3? Again, same thing is happening, yeah? So I do 1.5 times 3, that's the moles of oxygen atoms, but they don't ask for moles, they ask for the number of atoms. Yeah, so times Avogadro's constant. 1.5 times 3 times 6.02 times 10 to the 23rd. So that would be C. And what is the total number of ions and 0.5 moles of NH4 to CO3? This is slightly more complicated, so you need to know, you need to recognize, yeah, that this formula has two types of ions, and you would know it, we would cover it in structure 2. So this formula, it has two NH4 plus ions and one CO3 2 minus ion, yeah, which you cannot see well. Okay, so it has two NH4 plus ions and one CO3 2 minus ion. So it has 3 ions in total, yeah, 2 and 1. So then it means that it would have 0.5 times 3, that's the moles of ions, and times Avogadro's. So because they don't want the number of moles of the ions, they want the total number of the ions. So 0.5 times 3 times 6.02 times 10 to the 23rd, so that is AB. Now this one, what is the total number of moles of atoms in 0.01 mole of that? So they ask for the moles of atoms. So I know it's not A, it's not B. So if they ask for moles of atoms, that would be a small number. Yeah. Total number of moles of atoms. Okay, so how many atoms do I have in that formula? Because that's what they ask. They ask for the total number of atoms. So in this formula, I have one platinum, two nitrogens, plus 3 times 2, 6 hydrogens, and 2 Cls, 2 chlorines, right? So in total, it's 11 atoms. So I have 11 atoms per formula. So if I have 0.01 moles of atoms, I would have 0.01 times 11. Yeah, so that would be what? 0.11. That's the moles of atoms. If they asked me what is the total number of atoms there, I would multiply it by Avogadro. That's a D. How many oxygen atoms are there in 2 moles of copper sulfate times 5H2O? Okay, what do? We do 2 moles. How many oxygen atoms? How many oxygen atoms do we have? 4 from here, 5 from water, so 9 in total, times Avogadro's constant. So that's 2 times 9 times 602 times 10 to the 23rd, which is C. And the last one. What is the total number of moles? Which ones do we exclude? Total number of moles, so not A, not B. What is the total number of moles of hydrogen atoms are there in 1 mole of benzophenone? So I find the moles of hydrogen atoms. So I do 1 mole times how many hydrogen atoms do I have? 10. That's it. No Avogadro's constant needed here. Fine, fine. Okay. Next. Some definitions. Definitions might be a little confusing, but well, I don't know, you just have to deal with them. Yeah, so relative atomic mass of an element is the average mass of the naturally occurring isotopes of this element relative to the mass of the 1/12 of carbon-12 atom. So it's relative atomic mass, it's the average mass of all the isotopes. Remember how we did it in the mass spectroscopy topic? Yeah, so we averaged the masses of all isotopes, took the weighted average. So average mass of all isotopes relative to what? Relative to the mass of 1/12 of a carbon-12 atom. A relative molecular or formula mass of a compound, it's like the formula of the compound, the mass of the compound or a molecule relative to the mass of 1/12 of carbon-12. Or you can just say that MR, it's just the sum of relative atomic mass of all the atoms. So let's see. We find it from the periodic table. The most important part to remember for paper 2 is that the molar mass has to be calculated to 2 decimal places, just like it's written in the periodic table. For paper 1, no one cares. For paper 1A, no one cares because it's a multiple choice. You can round it if you want, but not here. Okay? Well, let's do one example. Calculate MR of the following compounds. Give the answer to 2 decimal places. So let's calculate MR of H2CO3. Was it H2CO3? Yeah, H2CO3. So what do we have? We have 2 hydrogens, so 2 times relative atomic mass. Yes, so that's this number, the bottom number, 1.01 plus 1 carbon, 1 times 12.01 plus 3 oxygens, 3 times 16. And whatever that is, 2 times 101 plus 12.01 plus 3 times 16 is 62.03. Right. If you have brackets, let's do this one. So if you have brackets, what do we do? So Mr of Al2SO43, nothing complicated. You just do it, just calculate the number of atoms of each element. So you have 2 aluminium, so 2 times aluminium is where? It's here, 26.98 plus sulfurs. We have 3 sulfur atoms here, so 3 times sulfur, 32.07 plus oxygens, 3 times 4, 12. 12 times 16. Okay, 2 times 26.98 plus 3 times 32.07 plus 12 times 16 gives me 342.17. Well, you got the idea. Okay, next. Formulas, calculating moles from mass. To calculate moles from mass, you do mass divided by MR. Yeah, M or MR, it's like the same thing. It's just molar mass with units, MR without units, but calculated in the exact same way. I think this formula now is in the data booklet, which is extremely generous. It is there, yeah, so you can use it, but highly recommend to memorize. That's like the most important formula in chemistry. Well, and then also if you're given moles, you can rearrange it to find mass. It's moles times molar mass. Let's see, so how many moles are there in 16 grams of water? So they want moles from mass. I use the first formula. So 16 grams, mass is always in grams. If it's not in grams, you have to convert it to grams. Divided by molar mass of water, so it's 2 hydrogens plus 1 oxygen. So it's 16 over 18.02, which is 0.888 moles. Or the opposite, how many grams are there in 1.25 moles of CO2? So you use mass equals to N times molar mass. So you do 125 times molar mass of CO2. Carbon is 12.01 and 2 oxygen, so 1.25 times 2 times 16, which is 55.0 grams. Uh, 125 times 44. Yeah, 55.0 grams. Next we need to know how to work with empirical and molecular formula. Definition. Empirical formula is the simplest whole number ratio of elements in a compound. But molecular formula shows the total number of atoms of each element in a molecule or a compound. So if I have C2H4 as a molecular formula, then the empirical one would be when you cancel the small numbers out by some number to get the whole number. So I can cancel these out by 2. So my empirical formula would be C1H2. For C4H10, I can also cancel them out by 2, so I get C2H5. For this one, molecular and empirical formula would be the same, yeah, because I cannot cancel anything out because there is nothing I can do with this one. And let's do this question. Deduce the empirical formulas for the following compounds. So I just have to cancel the small indices out. So for C3H6, I would get cancel out by 3, CH2. From C6H12O6, I get divided by 6, so C1H2O, and so on. Yeah, and so on. I'm not going to do those. Next, let's talk about how to find the empirical formula of compounds based on the percentage composition and relative molecular mass. So glucose contains 40% biomass of carbon, 6.67 hydrogen, 53.3 oxygen. Molar mass of glucose is 180. Calculate the empirical and molecular formulas. Well, let's do that. Okay, empirical and molecular. So what do we do here? We assume that we have 100 grams of a compound, which means that then we would have 40 grams of carbon, 6.67 hydrogen, and 53.3 grams of oxygen. So to find the empirical formula, I need to find the ratio of moles. That's what I would do. So carbon 40, hydrogen 6.67, oxygen 53.3. So these are grams of atoms. Then I divide them by relative atomic mass to convert to moles. Relative atomic masses are from the periodic table. Yeah, so 101, 1201, 16. And let's see. So I do 40 over 12.01. That's 333. This is 6.60, and then 53.3 over 16. It's 3.33. So I got these numbers. Then I divide them by the smallest to get the whole number ratio. So I would divide them both, all of them, all three of them, by the smallest number, which is 3.33. And I get 1 to 1. So I got the whole number ratio, which is 1 to 2 to 1, which means that my empirical formula would be CH2O. Yeah, so we found the empirical formula. Now let's find the molecular formula. So to find the molecular formula, what we do is we need to know the molar mass, yeah, and we know it, it's 180. So we find the molar mass of the empirical formula. So I find Mr of CH2O, and then I would divide the true formula, the true molecular mass, over the molar mass of the empirical formula, and this way I would see how many times heavier the true molecule is relative to our molecular formula. So MR of empirical formula is 12.01 times that plus 16, which is 30.03, and then you take the true molar mass, 180, divided by 30.03. And you have to get the whole number. If it's, well, it's like close to 6, it's, I mean, close to a whole number, that's fine. If it's something completely far away from a whole number, then you did something wrong. So this is 6, and which means that our true formula, so empirical, was CH2O, and then I multiply all of the small numbers, all the indices, by 6. So it becomes C6H12O6. That's molecular formula. That is molecular formula. Right. Let's do one more with not such good numbers. Let's do this one. A compound contains 73.99% of carbon, oxygen, hydrogen, remainder is nitrogen. What is the empirical formula? Okay, so I do the same thing. Carbon 73.99, oxygen 10.37, hydrogen 6.55, remainder being nitrogen. What does it mean? It means that it's 100 minus the rest. Yes, so 100 minus 73.99 minus 10.37 minus 6.55, which is 9.09, and then I divide everything by relative atomic masses. So this is 12.01, this is 16.00, that's 1.01. Nitrogen was 14.01. So let's divide 73.99 over 12.01. 10.37 over 16, 0.648. This is 6.49, and this is 0.649. Then I would divide all the numbers by the smallest, so by 0.648. And from here I get 0.648. That's okay. I got 9.5. That's too far away from 9, too far away from 10, so I keep it like that. This is 1, this is what? This is 10, right? Approximately. This is 10, and this is 1. So 9.5, we keep it because it's too far away from 9 or 10, and that's why I have to multiply all the numbers by 2 to get rid of the 9.5. So I'll multiply everything by 2 to get the whole number. So I would get 19, 2, 20, and 2. So C 19, H, not H, O2, H20, and 2 is my empirical formula. Here I multiplied by 2. If 2 doesn't work, multiply by 3. If 3 doesn't work, multiply by 4. So just find the number by which the smallest number by which you can multiply to get the ratio to whole numbers. Okay, that's it. Then analyzing combustion data. I did have a separate video on this, but I'm just thinking I will explain it here, but not this question. Let's do this one. I think I did it already on this channel, but just to keep it all in one place, let's do it. Okay, so then another way to find empirical formula, it's from, or should I maybe, you know what, no, I will not explain it. I will just link this type of questions. Okay, I have explained it already. So I have these questions in another video, so I will skip it here, but you can find it on my channel. It's calculating empirical formula from combustion video. If I remember, I'll put a link here somewhere. You can watch it there. Okay, so that was explained previously. Let's save some time. It's already 2 hours. Oh my god, I've never had such a long live stream ever. But guys, again, remember, if you need this type of information in your life, you have to let me know, because I'm not doing it again if I don't see any feedback. Okay, if you like it, just hit like, subscribe, leave a comment, send me a message so that I know that you're watching. Fine, then next, molar concentration. Mole per cubic decimeter always. Yeah, this cubic decimeter is non-negotiable for some reason. Just mole per cubic decimeter. They don't accept mole per cubic centimeter, meter, doesn't matter. Only mole per cubic decimeter. So moles, it's concentration times volume, or concentration, it's moles over volume, or volume is moles over concentration. Simple rearrangement, these formulas you need to know. Example, what is the volume of the solution that contains 0.95 moles of NaCl and has a concentration of 0.5 mole per cubic decimeter? So this is moles, this is concentration. How do I know? Based on the units. Yeah, mole per cubic decimeter, it's always concentration. And we need volume. So volume would be, I will use this formula, it's moles over concentration. So 0.95 over 0.5, which gives me 1.9, and the units are dm cubed, exact same units as in concentration. Next, I will skip those, you can solve them on your own if you want. What volume of the 1.25 mole per cubic decimeter solution of copper sulfate can be prepared from 150 grams of copper sulfate? So we know that to find the volume, we just use the formula. To find the volume, we need to do moles over concentration, but we don't have moles here. To find moles, we can use the formula that moles equals to mass over molar mass. So I will find the moles of copper sulfate first. Yeah, this is concentration, this is mass, yeah, because it's in grams. Finding moles, alright, so that's 150 divided by molar mass of CuSO4. Let's find it here. So copper is 63.55. Sulfur 32.07 one sulfur, and 4 oxygens. Oxygens you probably remember by now. So it's 150 over, let's see, 63.55 plus 32.07 plus 4 times 16, which is 159.6. Yes, and 150 over 159.6 gives me 0.94 0 moles. That's the moles, and we know that the concentration is 1.25. So now I find the volume of the solution, which is moles over concentration. So 0.94 divided by the concentration, 1.25. 0.752 dm cubed. Yeah, 0 moles over concentration. Yes, and if they asked, for example, to use it in cubic, to convert it to cubic centimeters, so to convert from decimeters to centimeters, you multiply by 1,000. So 1 cubic decimeter contains 1,000 cubic centimeters, so that's 752 cubic centimeters. Fine. The next one is a similar one. I will not do it. The next bit is the glassware to prepare solutions. Again, that's new, and I mean, we always had it in practicals, but it wasn't explicitly mentioned in the syllabus. Now it is, so let's talk about it. Right, so these are just different vessels to, to draw liquid or to store liquid. The first one is conical flask. So the conical flask, even though it has some graduation marks, we never measure volume with the conical flask. We use it, for example, for titrations. We use it to make solution, to store, like to, if you just want to dilute something, but never to measure. Volumetric flask, it's very precise. So it's a flask with a, if you see it, you see there is, I don't know if you can see it, but there is a graduation mark. So when you're making a standard solution, for example, if you need to make a solution with a certain concentration, so you calculate which mass of the solid you have to add, and then you add water so that the total volume is, for example, 250 cubic centimeters. So if you need to do that, then if you add liquid to this flask so that the bottom of your meniscus touches the graduation mark, that would be exactly 250 cubic centimeters. That's very, very accurate. So that's why we use it. Measuring cylinder, you could use it to measure volumes. It's not very accurate, not very precise, but usually we use it if we don't need to measure something really accurately. And we can also use it if, for example, you need to add something quickly. Like, for example, if you need to add 50 cubic centimeters of acid really quickly to the reaction mixture to stop the timer, well, that allows you to do that. Yeah, the measuring cylinder. The beaker, again, we never use it to measure volumes, even though it has some graduation marks. Pipettes, volumetric pipettes are also very accurate, so they have the graduation marks. Usually they would have, they would be for certain volume. And burette, it's almost like a pipette. So basically, if you need to measure 10 cubic centimeters of liquid, you go for a pipette. Okay? If you need to measure variable volume, you can use the burette. For example, we use a burette in titrations. It's when we have to measure the cubic centimeters that were dropped from the burette. Yeah. So the burette is just like a pipette, but it has you can't see it here, but it has different graduation marks, so different volumes could be measured, and it has a tap. So using this tap, you can control the flow of liquid. So you can open it, the liquid would drop down. You can close it, the liquid would stop flowing. The next bit is serial dilutions. Again, I'm not sure what we need to know about that. It's a new thing, but just in general, what is dilution? So dilution, it's when you take, you have a solution of something, and you add water to decrease its concentration. That's dilution. Yeah. And if, let's say, you have 100 molar, this M means mole per cubic decimeter. So if you have 100 molar solution, you can dilute it 10 times, decrease its concentration 10 times by doing the following. So you take 1 part of the solution and 9 parts of water. That's your 10 times dilution. So if you take 1 cubic centimeter of this solution and add 9 cubic centimeters of water, That makes it 10 times less concentrated, 10 molar. Then again, if you take 1 cubic centimeter of this solution and add 9 cubic centimeters of water, this becomes 1 molar, and so on. Yeah, that's serial dilutions. It's very handy to use when when we need to plot calibration curves, for example. And this is the next bit. Again, it's a new part of the syllabus. They did ask it in some options before, but not commonly in exams. Now they do ask. So, okay, so what's the deal with the calibration curve? Let's say you have some colored substance, for example, protein that absorbs UV or something. Yeah. And let's say you have a patient sample with the protein for which you want to measure the concentration. So you took a sample from the patient, there is a protein, you want to measure its concentration. How would you do it? Well, you do it using a calibration curve. So what you need to do to plot the calibration curve is you make a series of solution of that protein which you're measuring of different concentration. Yeah, so you make it yourself. So you take like an empty beaker with water, then you make a concentration of, for example, like 0.2, 0.4, 0.3, and so on. So you make different concentrations, known concentrations of your sample, and measure their absorbance. Absorbance, it's like how it absorbs light. Yeah, so if it absorbs light, some doesn't have to be visible light, but some light, you can measure it. So you take your samples with known concentrations, measure absorbance, plot the graph. Yeah, so all these points, they come from the samples of known concentration. You have this is called the calibration curve. Now you take your patient sample. Take the sample, measure its absorbance, and let's say the absorbance was like 0.52 or something, yeah? 0.52. So okay, so then you go this way and down. Yeah, so you see measuring the absorbance, like you can now find the protein concentration from your patient using the calibration curve that you have. Yeah, so you measure absorbance, then see when, like what value. So you draw a line so that it intercepts with the curve, and then go down. And this down line would show you the concentration of protein. Oh, whatever, it doesn't have to be protein, yeah, but the logic is that. That's calibration curve. Fine. Next bit. The next bit is Avogadro's law. Oh, and guys, I forgot to tell you, everything was SL. Yeah, everything in moles, everything we've done was SL. I totally forgot to tell you, but it's there. And also, hopefully, I will do the timestamps because you'll be lost without my timestamps. Right, Avogadro's law. To be honest, I have no idea why it's in structure because it's all about reactivity because we have to apply the ratios, which we haven't done yet. Following the syllabus. Yeah, I'm just a simple person following IB. Right, so what does it say? Avogadro's law says that equal volumes of ideal gases, and we haven't done ideal gases yet, measured at the same temperature and pressure have the same number of particles. That's the definition. What are the implications? I'll quickly explain the ratios, although it needs maybe some extra time later. It's in reactivity. Alright, so you have this equation. 2CO gas plus O2 gas goes to 2CO2 gas. What do the coefficients tell you? The coefficients tell you the molar ratio of substances. So they tell you that for 2 moles of CO, you need 1 mole of O2 to get 2 moles of CO2. That's how we normally use the ratios. Yeah, that's normal molar ratio from the balanced equation. Now for Avogadro's law, what does it tell you? So it tells us that if your molecules are gases, which they are, you can apply the molar ratio to the volumes. So we can say that instead of 2 moles react with 1 mole, we can say that 2 cubic decimeters of CO would react with 1 cubic decimeter of O2 to give 2 cubic decimeters of CO2. Yeah. So as long as the units of the volume are the same, you can apply molar ratio to the volumes. This saves you a great amount, like especially for multiple choice question. It can save you like 5 minutes. Yeah. Um, right. So let's see the example. What volume of oxygen is needed to convert 40 cubic centimeters of carbon monoxide to carbon dioxide? Yeah. What is the volume of oxygen? The volume of oxygen, how do, well, Again, you could convert 40 cubic centimeters to moles, then apply the ratio, then convert moles back to volume. But using Avogadro's law, we know that it's the ratio is 2 to 1, so it means that we would need 20 cubic centimeters of oxygen. That's it. Yeah, so just apply the ratio to volumes. That's it. And structure 1.5, the final bit, ideal gases. Okay, we're close to finishing this. Structure 1. Ideal gases, again, that's all a cell. What are ideal gases? So whenever we're talking about gases, we imply their ideal behavior. You don't need real gases. You don't have any formulas for real gases in IB. So we are talking, whenever we're talking about gases, we're talking about ideal gases. So what do? Ideal gases, they have like, they don't have any shape, yeah? They are like spherical molecules that are flying around randomly. They collide with each other, they collide with the walls of the container. All collisions are elastic, they don't lose energy. And the most important assumptions are these two that I wrote, yeah, the ones that they ask about. So first is that the volume of gaseous molecules is much smaller than the volume of the container. So we say if the container is, let's say, 1 cubic decimeter, the entire 1 cubic decimeter is, available for molecules to fly around. Yeah, so we say that molecules are kind of volumeless, which is wrong, but like that's our assumption. And the second assumption is that there are no intermolecular forces between gaseous molecules. That's everyone is laughing. My students always laugh at that because we spend so much time doing intermolecular forces. Everyone hates intermolecular forces. Well, for ideal gases, we assume there are no intermolecular forces. And then, based on these assumptions, they can ask you two questions. So they can ask, when do gases deviate, or the other way around, when do they obey the ideal behavior? So when do real gases deviate from the ideal behavior? Well, at low temperatures. Why? At low temperatures, your gases would not behave as ideal, because at low temperatures, the intermolecular forces, so the forces of attraction between molecules, would be too high, and we cannot neglect it. Yeah. So at low temperatures, intermolecular forces do not let us, say that these that gases behave as ideal. Because imagine water vapor. If it's vapor, well, it's pretty much gas, yeah. But if you drop the temperature to zero, it becomes ice. How is that an ideal gas? Yeah. So at low temperature, water does not obey ideal gas assumptions. It doesn't behave as an ideal gas. It becomes solid. And at high pressure. So at high pressure, gases would also deviate from ideal behavior. Why? What is high pressure? Well, at high pressure, you have a lot of molecules in a small volume. Well, like in a volume, yes, so you have some volume and there are a lot of molecules. And then in that case, you cannot say that the entire volume of the vessel is available for molecules to move. So the volume occupied by the molecules cannot be neglected because it's so cramped, right? So all the molecules are like the molecules occupy a significant volume of the vessel. These questions are usually multiple choice. Now, pressure, volume, temperature relationship. So if the gases have okay, so equal volumes of ideal gases measured at the same temperature and pressure contain the same number of particles. That's what we just discussed. And we need to know how to draw out the graphs for different, like 2D obviously, so only two variables, everything else is constant. Pressure, volume, temperature, pressure, temperature. They could ask some other graphs as well. I noticed recently, in recent years, they can ask any axis. But in general, if you know these three, then you more or less understand how to plot them. So from a pressure to volume, well, actually, again, this is a little bit out of context. Let's do it this way. I will show you the ideal gas equation. So that's the equation that connects pressure, volume, temperature, and moles. Yeah, let me explain this first. Yeah, I'll explain this first and then I'll go back. So this is an ideal gas equation. It connects, again, I switched the order around a little bit, but I hope it's okay. So again, that's SL. So pressure of gas times volume equals to moles times gas constant times temperature. So in this equation, the most important part is the units. So pressure must be either in kilopascals or pascals, and then volume would be in either cubic decimeters or cubic meters. That's for IB. If for some reason you're an A-level student and watching this, you are not allowed to use kilopascals and cubic decimeters, okay? It's only for IB. So you use either kilopascals together with cubic decimeters or pascals together with cubic meters. So you never mix them up. Okay? N is moles of gas, R is the constant that's in the data booklet 8.31, T is temperature in kelvins, so it's Celsius plus 273. But let's just look at this equation and go back to the graph. So how do we figure the shape out? So okay, so the equation is PV equals to N RT. So if they ask you to plot a graph P against V, so what do? So you need to rearrange mathematically this equation so that you have only y-axis on the left and x on the right. Yeah, so you do, I rearrange it. So P equals to 1, I divide both sides by V. Yeah, so 1 over V times N RT. If they ask you to plot a graph, they assume everything else is constant. So if they ask you to plot a graph P against T, they assume that N and T are constant. So you see this is your X, and not that, this is your X. Yeah, so it's 1 over X. This is your Y, and this is some constant. So you rearrange this and you see now the shape of the graph. Yeah, so it's Y equals to 1 over X. So that's hyperbola, so it's like going like that. Yeah, from math you should know the shape of this graph. Now, what if they ask you to plot V against T? Well, I do the same. So I have to keep V on the left on its own. So I will divide both sides by P. So I do V equals to N R T over P. So V is my y-axis, X is my and yes, it's 2.5 hours. I start drifting away a little bit. Okay, so V is my y-axis, T is my x-axis, and this is a constant. Yes, so it's x times some constant. Well, this is a straight line going from through the origin. Yeah, that's it. Well, and you can do the same with P against T. You'll see that it's exactly the same thing. Yes, we divide by V. This is y, this is x, this is a constant. You can try it out. Next, molar gas volume. So the equation that I just showed you, it works for all conditions. So no matter what temperature, pressure, and volume you take, it would work, yeah, no matter what temperature and pressure. But then if you have standard conditions, what does it mean? Standard conditions are conditions at 100 kilopascals pressure to 73 kelvins. So if you take these conditions, which are standard, then 1 mole of any gas would occupy the volume of 22.7 cubic decimeters. This is in the data booklet. So molar volume tells you what volume 1 mole of ideal gas would occupy at certain conditions. If you change the conditions, the molar volume would change as well. Yeah, so for IB, usually these are standard conditions. If you're solving older questions, they can give you molar volume for room temperature and pressure, for example, so they would tell you. And if you know the molar volume, you can use the formula that moles equals to volume over molar volume, or rearrange it to find the volume, which is N times molar volume. Example, how many moles are there in 14 cubic decimeters of hydrogen gas at STP? Well, we need moles, so I use the first formula. 14 at STP, so at STP we know the molar volume is 22.7. 22.7, that is 0.62 moles. What is the volume of 0.5 moles of CO2 gas at STP? N times molar volume, so 0.5 at STP, it's 22.7. 0.5, that is 11.4 cubic decimeters, right? Because the molar volume is cubic decimeter per mole. And next, let's go back to the ideal gas. So we discussed the units, we discussed the formula. So yeah, so basically whenever the conditions are not standard, you can use this equation to rearrange. Now units conversion. So 1 cubic meter, it's 10 to the power of 3, well, 1000 cubic decimeter, or a million cubic centimeters. Question: what volume is occupied by 2 moles of ideal gas at temperature 280 kelvins and pressure of 100 kPa? So yeah, there is just end what I'm blocking. Conditions are not standard because 280 kelvins, it's not 273 kelvin, so that's not standard condition. So that's why I cannot use molar volume. I have to use PV equals to nRT, and I rearrange it to find the volume. So N is 2, R is 8.31, temperature in kelvins 280, and pressure 100. Well, I keep it in kilopascals. If I use the pressure in kilopascals, I'd get the volume in cubic decimeters then. Yeah, because remember, kilopascals correspond to cubic decimeters. Okay, 2 times 8.31 times 280 divided by 100, it is 46.5 cubic decimeters. Right. Next. 1.25 grams of an unknown gas occupies 895 cubic centimeters at pressure 100 kilopascals and temperature 17 Celsius. So just let's change this. Find molar mass, yeah, because usually that's how it's worded now. So find MR of the gas. Yeah, let's do it this way. Right, so this is a very, very typical question, and it is worth 3 or 4 marks. Usually before that, they would ask you to find the empirical formula, then using this data, you would find MR, and then they ask you to find molecular formula. Very expensive questions. Let's solve it. So we know the mass. We obviously don't know the MR. That's what we need to find. So to find molar mass, usually we find molar mass from the periodic table, but here it's not possible because we don't know what the gas is. So we can rearrange the moles formula. We can do molar mass is equal to mass over moles. That's what we would do. And how do we find moles? We would find it from the PV equals to nRT expression. Yeah, so I will rearrange this to find the moles. Then I would plug in the moles into the first expression. Fine, fine. Okay, let's do that. So, okay, moles. It's PV divided by RT. So pressure, kilopascals, I would keep it. Volume, since I used the pressure in kilopascals, I have to convert volume to cubic decimeters. So that is 0.895 dm divided by R is 8.31. Temperature 17 Celsius, so 17 plus 273 gives me 290 kelvins. Yep, 17 plus 273. Okay, so 105 times 0.895 divided by 8.31 and divided by 290, which gives me 0.0390 moles. That's moles. And then I plug it into the first equation to find molar mass. So that's mass divided by moles. 32.1. That's a good molar mass. If you get something like 32,000 or 0.0032, that means that you messed up the units. Done. And the last, okay, congratulations, the last page. Combined gas law. Combined gas law. So whenever you have, okay, so important thing. The important thing is that you can use this law when moles of gas do not change. Okay, and I think was it in the specimen paper? I think it was in the specimen paper. They changed the moles, and everyone used this formula, which you cannot use because it's this formula you can only use if the moles of gas do not change. Yes, so moles must be constant. So it is in the data booklet. So basically, you can use this formula to quickly find out how the volume, pressure, and temperature change. One of those change if you change other conditions. Yes, so for example, you have a gas at conditions 1, then you change pressure or temperature, and you want to find the new volume. That's the formula you have to look at. Yeah. Let's see. So at which temperature in kelvins, assuming constant pressure, is the volume of fixed mass of gas at 1 to 7 Celsius doubles? Right, so you could think about this question in two different ways. You can think about it mathematically, so you can just plug everything into this expression and calculate the temperature. Or you can think logically, but to think logically, we still need to calculate this temperature in kelvins, because in Celsius the law doesn't work. So that's 400 kelvins, okay? Okay, so let's think. So at which temperature, at constant pressure, the volume of fixed mass of a gas doubled? Yeah, so you do something with temperature and the volume of your gas doubles. What do you have to do with temperature to double the volume of gas? Well, obviously you have to heat it, right? So if you think about a balloon with gas, so if you want to for it to expand, do you have to heat it or cool it down? You have to heat it. So if you want to double the volume, you have to double the temperature. So the answer is D. But let's solve it mathematically and check if we're right. So to solve it mathematically, I would, it takes ages, but let's see. So I would have to write conditions for like condition 1 and condition 2. So for condition 1, so that's my initial conditions of the gas. So at which temperature, assuming constant pressure, so P1 equals to P, the volume of a fixed mass of gas doubles. So let's say V1 equals to V, and temperature 1 equals to 400 kelvins. Yeah. Now in conditions 2, what do we have? Pressure is the same, so P2 equals to P, yeah, constant pressure. Volume, V2, it's double of V1, yeah, so the volume must increase, so it's 2V, okay, fixed mass of gas, so the volume doubled, yeah, so the new volume is, oh no, wait, the other way around, new volume, yeah, no, that was correct. That was correct. So new volume, it's double the previous one, so 2V. Yes, all good. And T2 we want to find. Yeah. Okay, so these are two conditions. Now let's plug everything in. So I'll just plug all the letters here. So P1 is P, V1 is V, T1 is 400 equals to P2 is P, V2 is 2V, and T2 is what I need to find. Yeah, that's T2. And then I rearrange it, so to find T2. So T2, you know how to find it, it's crisscross. So you basically, from math, yeah, so just crisscross these two numbers, like you multiply them and divide by the number that's opposite to T2. So you do 400 times P times 2V divided by PV. So P cancels, V cancels, and you end up with 800 kelvins. Yeah, that's a long way to solve it, but if you don't understand like what you have to do with the balloon, you can do that. Yeah, so either way you get the correct answer. And one more question. A fixed mass of an ideal gas at 27 Celsius. Again, just right away convert it to kelvins, yeah, because all those doubles something halves, it only works for kelvins, not for Celsius. And that pressure has a volume of 100 cubic centimeters, which change doubles the volume of the gas. Let's think again. All the numbers for Celsius I convert to kelvins right away. So 327 kelvins, and this is plus 273. This is 600 kelvins. Okay, so question, which change doubles the volume? Which change doubles the volume? So heating gas at a constant pressure to 54 Celsius. This answer option you can exclude right away without thinking, because what did they do? They doubled the temperature in Celsius. That's never the answer, okay? That's never the answer, so not A. I won't even think about it. I can see temperature doubled in Celsius. That's wrong. Okay, now heating the gas at constant pressure to 600 Kelvin. Well, that's doubling in Kelvin. Let's check. So which change doubles the volume? Well, yes, if we heat, the gas, if we double the temperature, the volume would double. Yeah, so at constant pressure. So I'd say B, but let's check the rest. Increasing the pressure at a constant temperature. So imagine if you have the gas at certain pressure, then if you increase the pressure, what would you do? You squeeze your balloon, right? So you increase the pressure. What happens to volume? The volume decreases, so not C. Heating the gas to 54 Celsius and increasing the pressure to that. Well, again, that's doubling temperature. I wouldn't even think about that. Yeah, but if they double the temperature in kelvins, let's see, if they double the temperature in kelvins, for example, then the volume would double, but then they double the pressure, the volume would half again, so the volume wouldn't change, so not D. Okay, we are done with structure 1 completely. I let you go. So if you want this to continue these live streams, you have to let me know. Okay, this was extremely exhausting. 2 hours, 43 minutes. It's like 3 of my lessons without a break. Today I had time, yeah, but if you want me to continue, I would really have to set the time aside because today it's like not my day off, obviously, but I had the time to take from my teaching, from my regular teaching, to do this live stream. I hope it was helpful. I understand that probably I'm doing this during the summer, so probably you would watch it like before your exam or something. So if you need more live streams, you have to let me know. You have to like this video, you have to watch it, you have to send it to friends, you have to leave comments to tell me that you need more. Yeah, and if this was helpful. If not, that's fine. That's fine. I understand. Not everyone wants to study chemistry. So I let you go. If you have any questions, if you have any if you have any questions, if you saw any typos, any mistakes that I made, you can leave the comment so that everyone knows. Because I'm not going to rewatch it. I'm not going to rewatch it. And if you have any suggestions on other topics, so some smaller topics that I should cover, also feel free to leave a message or to leave a comment. See you next time.